Morning, everyone out there in the world. Ken Hudson here, along with Stella and Sebastian, and it looks like Woody is here. Francois Cochard stepped away for a second, but good morning.
Yeah, Mike.
Good morning, afternoon, or evening, or night.
Hello, Woody.
Hello, Francois. Tony, looking good. Hi, Drew. Hi, Stella.
Hi, how are you guys?
Good. Hi, Sean.
Good morning.
Good morning.
I think we need Tony to say something here so he fills the screen, because we need a closer look at that shirt for a minute.
Well, I saw the tie-dye. I saw the tie-dye astronomer, and I thought, how about the English flower?
There you go. Wonderful, wonderful.
That's great, Tony. Love it.
I hope she's going to be online as well, just to match your shirt somehow. Wonderful. So where are we all from? I am in Cambridge, Massachusetts. Ken is in New Mexico. Sebastian, Argentina. Drew, you are stuck in New Mexico, right? Yes. Francois, you're in France. Tony,
Yes.
where are you joining us from?
I am on a little wet rock in the North Atlantic called the UK.
Ah, still there. Okay.
But it's beautiful weather at the moment. It's
Wonderful, wonderful.
Cool.
Sean, where are you joining us from?
Beautiful Southern Oregon.
Oh, how's the weather there? He's going to say
Well,
perfect.
it was summer up until yesterday, and today it's winter.
Oh, wow. And who knows about tomorrow, right?
Yeah.
We
And
already
we-
have people from Myanmar, Peru, France.
Myanmar, Peru, France, Rhode Island.
Julio Vanini de Lima in Spanish.
Hello, everyone. Good morning, Barbara.
Sebastian, where are you from in Argentina?
Buenos Aires, the capital city.
Okay, I've been in your lovely city of Mendoza.
Oh, it's very nice and very clean. It's the cleanest city of the country.
Is it?
Yeah.
It's beautiful.
Well,
Yeah, it is beautiful.
We still aren't allowed to travel here within our own country for 8 months already. So until December 1, we are a strict lockdown here.
Mm.
Well, I see people from Arizona, Florida, Trento, Italy. Let's see here, Charlotte, North Carolina, St. Simons Island, Georgia, Quebec, Canada, Quincy, Massachusetts, another Quebec. Awesome. Santa Fe, not too far from me, Pakistan and Belgium. Other person from France, Cornwall in the UK. Actually, it looks like we have a couple of people from Cornwall in the UK.
It's where my name comes from. So I'm not down there. I'm from the opposite end of the country, way up near Scotland. But apparently my dad comes from Cornwall.
Oh, how cool.
Never been there.
Someday.
Yeah.
Yeah.
Well, it looks like if you go there, there's a couple of people that you could probably share a pint with, I'm guessing. So
Absolutely.
Are we live?
Yes,
We
we
are.
are live.
So I didn't get any email with the breakout Zoom meetings.
I think you should have gotten one for panelists, a panelist specific breakout meeting document. But let me see if I can forward you from my email.
Yeah, Buckheim too. You're right. I didn't get one to attend anybody else's breakout.
Well, I guess you're not attending anyone else's breakout.
Only mine is important.
Only yours.
I got one for mine. Yeah.
So Ken, do you mind just forwarding that email to everyone?
Yeah, I'm going to forward this to everyone. And for those who are panelists, keep in mind that your procedure for the ones that you're hosting is different from the other ones, but let me forward this to you. So
I think that, weren't there 3 of them? 1 for the panelists and 2 for the breakout sessions?
That's right.
1 for today and 1 for tomorrow.
well, the stuff for tomorrow, I do not believe has gone out yet, although
It hasn't. One day at a time.
yeah, we're trying to
So
keep
yeah,
simple.
there's a question on the chat, what breakouts? So bear with us for those who are attending. Ken will remind everyone what's happening today.
Yes,
so let's
I
wait
will
until
give a
everybody
little
comes.
update in just a second.
Yep. Yeah. It's so good to see you all though.
It was a good day yesterday. I enjoyed it. I think people really got a lot out of it.
Yeah, I agree. I agree.
We can
My
give it
coffee
another
arrived.
couple of minutes here to see if we get more people. And then I'll give, I'll do my best to summarize the process involved for the breakout sessions. But if I screw it up along the way, we have Stella here to help me out, and we've
To
got
fix it.
Sebastian, and between all of us, we'll work this out. This is kind of like landing a person on the moon. You know, this is,
It takes a village.
yeah, it takes a village.
Very nice. Well, it's wonderful to see all of you.
I have to say that I really appreciate Stella and Lindsay for signing on to this process, because early on when I told them that I wanted to have breakout sessions in Zoom, this was months ago that I brought it up. Nobody had that much experience with Zoom yet, and we weren't totally sure how we were going to do it and how it was going to work, but you know, they jumped right on and were willing to participate from the get-go, which is amazing, and I appreciate it. And now I'm going to cross my fingers and hope that it actually works today. So, but we'll talk about it in probably another minute. I'll give everyone another minute to join, and then we'll get going.
It's gonna be perfectly fine. We're pros now. We know our stuff. And we've had parallel sessions in the previous workshop as well, and they went spectacularly well. It was beautiful, actually, last weekend. So I'm very positive for tonight. And actually, there's lots of very interesting things to talk. I mean, my problem is that I don't really know which one to go to. I'd like to go to all of them.
Yeah, that's the tricky part. But
yeah.
The good thing is we're going to record these sessions, so that will help. They'll be available later on. So let's go ahead and get started. And as always, I'd like to say thanks again, but instead of going through the list of names, I just sat down this morning and quickly added up what I think are the number of people who were involved to make this happen. And if you take the panelists, you take the AAVSO staff, you take other people that were involved, the scientific organizing committee, et cetera, we probably have at least 35 people that were required to make this happen. So that's a lot of people coming together. And again, a big thanks to every one of them. So let's get started. We have an exciting day today. This is a day devoted to hardware, which I think, I don't know, it always seems like everybody's the most enthusiastic about hardware, although I think software is pretty cool too. And tomorrow is a day, yeah, Tom Field's putting his thumb up. Tomorrow is a day focused on software. And but today we're going to do hardware. We have two great presentations to start out the day on the UVEX. And I'm very excited about both of those presentations. The UVEX is going to be an amazing piece of hardware, so that will be fun. And then after that, we're going to do the breakout sessions. So here's how that works. First of all of the attendees should have received a PDF document last night that lists out the various breakout sessions and includes a URL that you put into your browser to go to the breakout session of your choice. Now, on some email systems and some browsers, you should be able to click on that link. Other ones, you may have to copy and paste that link into your web browser to take you to that particular meeting. But in any case, you can either click on it. I understand that in some operating systems, you should be able to drag and drop it to the URL line, but just follow that URL to the session that you want to do. Now, if you want to go to the Lhires session, let me get my notes here. If you want to go to Lhires, you don't have to do anything at all, because Lhires will use this Zoom feed that we're on right now. So after the second UVEX presentation, we have a break, and then those of you who are going to the Lhires III presentation with Francois don't need to do anything. You'll be where you need to be. And by the same token, after the second break, those of you who are going to the Lisa presentation still don't need to do anything, because that presentation uses the same link as this one, the main webinar. So for those people who are going to Lhires and Lisa, life is easy. For the rest of you that are going to Star Analyzer or ALPI in the first parallel sessions, or DIY and a shell in the second group of breakout sessions, you will need to go to a different URL, and that URL will be specified in your document. So hopefully that's clear and understandable. And with that, I think I'd like to go ahead and get started today with our first presentation, which is done by Drew Chojnowski. Drew is a friend of mine. I met him here in New Mexico when he was a grad student at New Mexico State University. Now he's a postdoc at Montana State University in Bozeman, although because of COVID, he's still here in New Mexico, and he'll be presenting from Las Cruces, New Mexico. But Drew is a really interesting person for an amateur spectroscopist to meet, because Drew spends all of his time, as far as I can tell, doing spectra. Drew sits in front of a computer terminal looking at spectra all day long, and basically he can tell you anything you're ever going to want to know about spectra. It's pretty amazing. When he's not doing that, Drew does rock climbing. So he's an interesting guy. And with that, I'd like to turn it over to Drew, who's going to tell us about the science case for the UVEX. And Drew, when you start, you can go ahead and share your screen.
All right. Thank you, Ken.
Just one thing to remember, people, that they have the Q&A box at the bottom to ask questions if they want, and we will read them later.
Yes, that we'll do that the same way we did it yesterday. And Drew, for your information, the only time I'll interrupt with questions is if there's something that seems urgent. Otherwise, we'll save up the questions for the end, and then I'll read through those and ask you the questions verbally towards the end.
Okay. Sounds good. Let's see. All right, can everybody see that?
Yes, we can.
Great. All right, so I'm Drew Chojnowski. As Ken mentioned, postdoc at Montana State, but not actually at Montana State. So I'll just start with a little introduction, which Ken already summarized. But so I graduated earlier this year from New Mexico State, and since June, I've been working for the Sloan Digital Sky Survey, fifth installment. Commissioning scientist David Nidever, who's actually a friend of mine from when I was at Virginia. And as Ken also mentioned, I was planning to move to Bozeman and made a strong effort in July to do so. And then COVID started spiking, both here in New Mexico and in Montana. So sadly, I'm still here in New Mexico enjoying the beautiful sunny weather. And so prior to that, I got a BS in physics and astronomy from Texas Christian University. Was not fortunate enough to make it into graduate school that year. So, but I was very lucky to get a job working for the Sloan Survey with folks at Virginia, and David Whelan, who's going to be speaking tomorrow. I met him while I was there also. And so, as mentioned, I got my PhD just earlier this year. The topic was H-band spectroscopy of exotic massive stars. I'll talk a little bit more about that in a bit. I am definitely interested in almost anything spectroscopy, but I really like things that are weird and that defy explanation. So things like AGN quasars, EE stars, rigidly rotating magnetosphere stars, chemically peculiar stars, RRMs in there twice, luminous blue variables, etc. And so when not doing that, I do love climbing in the mountains. So that is a photo of me over here doing something very dangerous. And I do have a prop, so I'm going to try to stop share really quick. So for anyone who's interested in the 3D printing aspect of this, this is my prop. This is the Oregon Mountains where I climb. And so this is like a ridge, a narrow ridge of granite peaks. It's about 10 miles long. Graduate student friend of mine 3D printed this for me, and I think it's pretty neat. How do we go back? Okay. So what do? I work for the apogee component of SDSS. So this is the Apache Point Observatory Galactic Evolution Experiment. It started out on the 2.5 meter telescope, the upper telescope on the right that you can see. And that is the telescope in New Mexico, not far from where Ken and Joe and among others here live. And then a few years ago, we thought this was such a good idea that, and we wanted to see the southern part of the Milky Way. So we worked out a deal with the Chileans to install a second duplicate apogee instrument on the LCO 2.5 meter, which is the telescope in the lower right of your screen. To show you what these instruments look like, it looks like a large casket. It's huge. It's not anywhere near the telescope. They're in a separate room underneath the telescopes, and then they're connected to the telescopes by a very long fiber run. And so these are fiber spectrographs. We observe 300 targets simultaneously at fairly high resolution, R 22,000 or so, and very long wavelengths. So for those of you who are already doing spectroscopy, you'll look at these numbers and say, wow, those are high. And yes, they are. For that reason, we don't use normal CCDs. We use infrared detectors. Maybe one day we'll have a near-infrared amateur spectrographs. That'd be great. But so we've observed about 1 million stars in the Milky Way since 2011. And we've been using this kind of primitive plug plate system where large discs of aluminum have holes drilled in them and fibers plugged into the back, and the holes are drilled at the position of stars. So each plate is customized to a certain part of the sky. But during SDSS 5, the big new innovation is that we're going to have robot fiber positioners. So we'll no longer have plates. We'll have little bitty robot arms that move the fibers around as we move around on the sky. And we'll be using the optical BOS spectrograph simultaneously with apogee spectrograph on both telescopes, and observing things like quasars and AGN with optical, and stars with the H-band instrument. To show you what apogee data look like, this is a spectral type sequence that I made years ago. The vast majority of targets that apogee observes are similar to the red and orange and yellow lines in this plot. So these are cool red giant stars. They're everywhere in the galaxy. they're fairly bright, and we can get really accurate radial velocities for them, as well as stellar parameters and chemical abundances. But as you go up to hotter temperatures in this plot, you'll notice that there's fewer and fewer lines. So these big wide lines are hydrogen lines, not the Balmer series that you're used to looking at, but actually the bracket series. And as you go up to O stars, there's pretty much nothing there. And these stars happen to be really useful because we have problems in the infrared, such as caloric absorption and air glow emission. And this causes a lot of junk to be in your raw data. And so we use these hot stars to calibrate that stuff out and end up with nice spectra. And so I actually work with the hot star sample. We target the stars randomly, and so we get a mixed bag of things, including a lot of BE stars and a whole lot of chemically peculiar stars. And you find the BE stars through their hydrogen emission, and the chemically peculiar stars by heavy element lines, including cerium element 58, which is our heaviest element lines that we get in the H-band. And so I've been making a living off of this sample for the past few years. Okay, so why am I here? I'm a big promoter of citizen science. Very excited about it, very excited about this conference. I was fortunate enough to be a speaker at the past few conferences. So in 2018 in Mayhill, that was very small. It was very nice. It was at Joe Daglin's house. The next one was in Las Cruces, much bigger, much more serious at a hotel near here. And so I was introduced to Ken and Joe by a common friend, Thomas Ravinius, and I think three of you were attending a meeting in France about the BE star spectra database, if I'm not mistaken. And to be honest, yeah, I just want you all to buy spectrographs and give me data. And I'll be happy to put anyone who's interested in working on any projects on the paper. And this has already happened numerous times, and including several papers dealing with what you see at the right, which is Haynes-Voorwerp. I'm sure many of you are familiar with this object. It was discovered by a Dutch school teacher participating in the Galaxy Zoo project. And when astronomers first got a look at this, no one had any idea what was going on. It's very, very strange. There's this nice spiral galaxy, but then there's just a large blob of oddly colored gas, not very close to it and not necessarily connected to it. And so this was a mystery for a while. We now know that the galaxy above the blob of gas was a quasar in the relatively recent past, but it has apparently burned out basically, but when it was an active quasar, there would just happen to be a cloud of gas below it, and it torched it, and the gas is still glowing as a result. I got involved mostly because we wanted to find more things like this to see if we could in the Cylindrical Sky Survey imaging. And so we enlisted a group of hardcore Galaxy Zoo participants who looked at images of many, many thousands of AGN. What they came up with was the Voorwerp cheese. Oh, and I didn't mention that Voorwerp is Dutch for object, so it's just Henny's object. And Voorwerp cheese is the diminutive of this. So we didn't find anything exactly like that, but we did find these things, which I think are some of the coolest images HST has ever taken. Amateurs are directly responsible for these images having been taken, having found these really good candidates in the Sloan survey imaging. And probably my favorite here is the one in the upper left. We call that the teacup, because it has this large ring of highly ionized gas that looks like the handle of a teacup. So moving on to spectroscopy, I want to try to plug citizen spectroscopy as much as possible because I've had a lot of fun over the past few years with Joe and Ken and David working on various projects. And the best example of this is the case of HD 63021. This was a target observed by David Whelan, who's doing a general survey of A and B type stars. This one stood out as unusual because it's an early A type star, but it has hydrogen emission, which is not out of the question. The BE phenomenon does extend down to A star type temperatures, but we got a few spectra of this thing and noticed that it was highly variable, and that other interesting things are in emission, like these iron lines, the calcium-2 triplet, some oxygen lines, and various things, and strangely a helium line, which is very hard to put into emission for an A-type star. We also then realized it was an X-ray source, which is also unusual, but despite these aspects, no one had ever really looked at this star. And so we wanted to do more, but we didn't really have the resources to do it. But thankfully, Joe and Ken were willing to observe this target numerous times. And so this plot over here shows H alpha emission profiles from data taken in basically 2 observing runs, but over 3 months. And you can see that the emission is highly variable. It's very chaotic, from broad single peaked things to asymmetric single peaked things to double peaked to very double peaked, etc. And from this data and also some spectra that I got, we also noticed that there are 2 sets of absorption lines in the spectra. So this is a double line spectroscopic binary. And thanks to all this data from Joe and Ken, and we actually asked them to tune their Lhires spectrographs to a different spectral range for the radial velocity monitoring, which I'll get to in a bit. But we were able to determine an orbital solution for the system, finding that the companion star is probably some kind of M dwarf or something, and it is essentially, but the A star is accreting mass off of the M dwarf, and this is leading to the emission. It's apparently not a constant fueling rate because the emission is quite variable, and the stars are very close to each other in a 3-day orbit. And so this is going in a paper that is soon to be resubmitted by David Whelan. This figure shows the silicone 2 line that we asked Joe and Ken to change the wavelength range to cover, and in the same wavelength range, we're also able to get lines for the secondary star. So this iron line, for example, is a good example of a line that's made by the less massive star. And then to the right is a Keplerian orbital solution for a circular orbit. The red points are the companion star. Blue points are the A-type star. So this was a really fun project. There's probably more to be done on this target, but moving on. A much more recent example has been this sample of AM/FM stars that I'm working on. So these are chemically peculiar stars. Unlike most chemically peculiar stars, these are non-magnetic, and the chemical peculiarities are not very well understood, but empirically we know that it's related to binarity. So something like 90% of this kind of star are known to be in binaries. And for the vast majority of them in the spectra, one set of lines will be stronger than the other or different than the other. You will be able to tell which star is which, but not the case for this one. So the figure to the right shows the apogee spectra of this star, and the red lines indicate the position of sulfur lines. And for a single star, these would just be one Gaussian, but you can see that there are 2 components moving around. So this is what a double line spectroscopic binary looks like. In this case, when the lines are separated, they look exactly the same. And the same is true for all of the lines in the spectra. They have identical equivalent widths, depths, everything. You can't tell which star is which. And unfortunately, with the apogee data, we don't get like a whole bunch of spectra each night. We get a spectrum 1 week, and then maybe one a month later, maybe one 2 years later. And so it's very difficult to piece these binaries together and figure out what's going on. And so I have a sample of about 10 of these where the two stars are identical, and I'm struggling to get an orbital solution. So I asked Joe to observe some of these, and he's been doing that over the past week. And so at the right, we can see his optical data covering those silicone lines that I was talking about earlier. And several of these are 4 observations in a single night. It was exactly this kind of data that was needed to figure out this system. And so I did the other day, and Joe's data also allowed me to realize that this is actually a triple system. So I was close to getting the orbit correct using the apogee data, but the thing about this system is you see the 2 stars in the spectra, and if there was not another object, this gray line in this plot, this gray horizontal line, would be the average velocity of the star. So that would be the center of mass velocity of this binary. However, for this one, if I were to plot the actual measured rate of velocities, this gray line would be a sine curve. So these 2 stars are actually orbiting something else. And upon realizing this, I just took the average of the rate of velocity data points for the 2 stars and picked an arbitrary value and said, okay, well, the average always has to be this. And so doing that, you get this nice orbital solution, fairly short period of 10 days. And as expected, the masses are identical. So with an inclination angle dependence, they're about a solar mass each. Oops. Too fast. And just yesterday, Joe sent me more spectra for more of these, and I was able to get 2 more orbital solutions. So the filled endpoints here are the data from Joe, and everything else is the apogee spectra. And this one is interesting because the one on the left, particularly useful data points are when the 2 components from the star are overlapping. So when they're at the same rate of velocity. And that point, along with this point, made it very obvious what was going on with this orbit. And so very happy about that. And as a third example, this is something that many of you out there probably contributed spectra to. HD 6226 is a classical BE star, and it's a highly variable one, as you can see from this time series data over here. From epoch to epoch, it changes from the appearance of a normal B-type star with no emission to a BE star with H alpha clearly in emission. And I'm pretty sure this is probably the richest data set for a BE star ever. Many hundreds of spectra. And this is great. And one of the cutest things about this project is that the author of it decided to 3D print these the H alpha line profiles. So this is the 2017 run, all of the data from the 2017 3D printed onto this little thing. And he actually included these images in the paper. I'm not sure that's going to get past the referee. But if anyone did participate that and are interested in having access to a 3D printer and want to make your own, there is a file for that. All right, so moving on to what we're actually here to talk about, UVEX. So UVEX is the Ultraviolet Explorer. It's a compact spectrograph, simple design, very interesting capability of high sensitivity to the UV down to the limit that is possible with our Earth's atmosphere. This talk is probably a little outdated because I was not aware that these will actually be manufactured and sold rather than just a DIY project that can be 3D printed. But if you want to save some money, you can still 3D print these. I think it's something like $750 to get the materials to 3D print them. There's a wide range of spectral resolution possible with this instrument. I think there's something like 6 gradings available now. And I also wasn't aware, but there's higher resolution grading. I'll get back to that at the end of this. But Francois or someone will show you an actual example of what they look like now, but this is what I found. So very compact instrument, goes right on the back of a telescope, can fit on a quite small telescope. So getting to the science applications, I think the most obvious one is spectral classification. So if you look at the image to the right, this is what your data from this telescope, from this instrument will look like. No, I'm just joking. This is very old photographic plate data, but this is how spectral classification generally works. You look at various lines in the spectra, say, and deduce the temperature and luminosity of the stars. So the temperature classes are the OBA, FGKM, and then for luminosity, we have main sequence, subgiant, giant, bright giant, supergiants, and less used hypergiant, which is the 0. And we try to do this with apogee spectra in a kind of a different way. So if you have high resolution spectra of stars that are slowly rotating with a lot of lines, you can actually make synthetic spectra and just fit those to your observed spectra. So in this figure, the red line is a model synthetic spectrum, and the black line is the observed spectrum. And it may be hard to tell, but I can guarantee you that it's a very, very good match. So this is a K giant, and the parameters you get are listed here. You also get chemical abundances for numerous elements. However, if you try to do this for weirder stars, it breaks down. So down here on the bottom right, we have the spectrum of a E bracket E star, and you can see that all the lines are in emission. There are no absorption lines. We have no models to deal with this in our apogee synthetic spectra grid. And so the red line that's been plotted over there is just nonsense. It gives it a temperature of 3000 Kelvin, which is silly. So things break down for hotter objects, especially in the H band. And I find spectral classification important for knowing what we're looking at and trying to correlate various things with stellar parameters. And so I spent a lot of my time trying to classify chemically peculiar stars in the H band. And this is about the best I can come up with. So at the top, you have a normal like A-type star. Then going down, you have a Mercury manganese star. These are very weird, very rare stars that have extreme Mercury and manganese abundances. We don't get any Mercury lines in the H band, but we do get these very strong manganese lines. So those are easy to identify. Things get more complicated when you go to magnetic chemically peculiar stars and then AM/FM stars. They're pretty similar, but there are some differences. These magnetic ones have chromium lines and other heavy element lines, whereas the AM/FM stars just have the lines typical of like an F-type star. And one unfortunate thing about the H band also is it's very unexplored. So the vast majority of these lines in this spectrum are unidentified. We can't match them up with anything in available atomic line lists. I've tried to do this for the E stars in the H band too, and is quite hopeless. So all you get for early B-type stars is hydrogen lines. So these vertical gray lines indicate where the hydrogen lines are. And for the BE stars, they're all in emission or these weird shelf profiles. So we really can't do much at all to classify these stars in the H band. There are some other emission features for metals, and again, some unknown lines. But we're pretty much just hosed in the H band trying to classify stars. Not the case in optical, and not the case if you can cover the Balmer jump. So the Balmer jump is this feature you can see in the right plot over here. It's at about 3646 angstroms. This is caused by the N=2 electrons and hydrogen becoming ionized. And so all of these transitions pile up here and lead to this big drop in the continuum level. It's quite sensitive to spectral type, as you can see there. So it's very strong for late A and early B type stars. I mean, late B and early A. The jump gets weaker for hotter stars and then also weaker for cooler stars. It's not as useful for cool stars because there are actually a lot of other lines there too, also contributing. As in terms of simply separating A and B type stars from like O type stars, it's extremely useful to see that Balmer jump. And I think this is one of the best aspects of UVEX. And you can actually get quite quantitative with your classification of stars using the Balmer jump. So these are figures from a paper by Shockroy. I failed to add as a reference in there, but I think this is Shockroy 2018. And if you look at the top panel, you can quantitatively determine the spectral type of a star using the Balmer jump by doing something like this. So these red lines are basically fit to the continuum after the Balmer jump and then before the Balmer jump. And these give this kind of envelope. And then if you just plop a line here where they intersect with the where the two continuum fits intersect, the difference between those gives this parameter called D star. And then if you take the average of those two red lines, which is this solid blue line, and take the difference of when that blue line hits the Balmer series or hits the continuum level, I guess, as compared to where the Balmer jump occurs, that value gives you this other value called lambda1. Anyway, the point is, if you plot these two values up, it results in a very coherent, quite coherent spectral type sequence. So we have hotter stars over here and cooler stars over here. There's quite a bit of spread, and you could use other methods to further narrow this down. But the Balmer jump on its own is a quite useful feature for classifying stars. Things get more complicated if you have a BE star, and particularly if you're looking at the BE star disk edge on, because the BE star disk will actually have its own Balmer jump. So in this figure, the red lines are indicating the Balmer jump of the actual star, but you can see that there's this extra one which they attribute to the disk of the BE star, which is essentially mimicking the outer atmosphere of like an A supergiant. So you have a quite large Balmer jump for the disk itself. But for normal B-type stars and A-type stars, you shouldn't see that. Okay, so now these are actually spectra from UVEX from Christian Buhl. 6 B-type stars here. Actually, these are all BE stars, pardon me. And these are great. The spectra are great because you not only do you see the Balmer jump in all its glory, you also can see the helium lines. And for this star in particular, you can see that this particular helium line that my cursor is on has a little feature to the right, which is actually a magnesium 2 line. And those 2 lines are very spectral type sensitive, as is the Balmer jump. So you get all of that with the UVEX in one shot. And then also these spectra also cover H beta. And so if you didn't see that for some of the stars, you wouldn't necessarily know it was a BE star. For 59 Sig, for example, if you didn't see the H beta there in emission, you might not know it was a BE star. And so, yeah, just looking at these, it's pretty obvious which are the hotter and which are the cooler stars. So just plopping down the spectral types on here. The hottest one is this guy. Doesn't really even have a Balmer jump. That's more of a, well, that's a Balmer positive jump. Let's call it that. Next hottest one, 59 Sig. Very little to no Balmer jump. And just proceeding. And here we have the 3 coolest stars. The Balmer jump looks biggest for this one. It should be bigger for Beta Lyrae, but Beta Lyrae is actually an exotic binary, so there's probably other effects going on in this one. 59 sig is as well, to be clear. And so another thing that I think is really cool about UVEX is that just by moving this little arm, if I'm correct, you can change your wavelength coverage and get the full optical spectrum. So not only could you observe a star and see the Balmer jump like earlier, you can also tune that knob and move down and get spectra that you get from Lhires. So this is the H alpha line in emission. There's a helium line over here, Earth atmospheric junk over here. And not only can you do that, you can go even further to the red, which is, I think, is really neat. So this is way out there. These lines over here are the Passion series lines. So far longer wavelengths than the bracket series line, next in level in the hydrogen atom. And you also get this nice O1 emission line. And the vast majority of spectrographs that I'm aware of that for example, I could apply for time on do not cover this range, and then especially not out to the range shown by this lower left spectrum. So this one is going all the way out past 10,000 angstroms, and it's very unique to be able to cover this range, especially for a spectrograph that also goes down to 3,200 angstroms. So it's very neat stuff. And so other obvious applications are the things you can do with just about any spectrograph. Well, I say that, but one example over here on the upper right is a Wolf-Rayet star. So it has these giant, broad emission features. And so one of the spectrographs that I have access to is an Echelle spectrograph, very high resolution. And if I were to try to observe this Wolf-Rayet star with that spectrograph, it would be horrendous. I would never be able to piece together all of the Echelle orders to put this spectrum together. This can only be done with the lower resolutions or slit spectrograph. Another thing that I thought was great is that in the bottom left here, this is a symbiotic binary, so all sorts of crazy emission lines and big molecular band heads. But down here in the extreme blue, they've actually detected these neon 5 lines. So there's one at 3,345 angstroms and one at 3,426 angstroms. And prior to looking at this spectra, I had only seen these lines in spectra of AGN. So, supermassive black holes that are producing very high energy UV photons. I think it takes like 5 electron volts to remove the 5th electron off of neon. So you need an extremely hard ionizing source. And so it's crazy that we're seeing those in a spectrum taken by an amateur astronomer. And then over to the right, bottom right is a luminous blue variable. So this is P Cygni, the best known luminous blue variable. And you've got all these crazy P Cygni profiles. And so there are just numerous kinds of objects like these that would be very interesting to monitor or just to observe and build up a library of oddball spectra. Do this with any spectrograph, but with the UVEX, you could get the full optical spectrum of all of these things. And before I finish, I just wanted to give a quick plug to AAVSO. So I am working on this sample of luminous blue variable stars that have been observed by Apogee. And what you see in the right of this plot are individual line profiles from actually the strongest lines present in the spectrum of this particular luminous blue variable. The first one is a hydrogen line. Second one is cerium. The next one is yttrium. So weird heavy elements. This kind of stuff has never been reported for luminous blue variable. But anyway, the point is that the left shows the AAVSO light curve. And so these luminous blue variables are defined by their extreme variability. And you can see that in the light curve. the magnitude of the star is changing from about 8.8 to about 9.3 over the course of this portion of the light curve. And I plopped some symbols onto the light curve for each of the apogee spectra, showing where they occur in the variability cycle of the photometric variability cycle. And there's not a whole lot of clear correlations here, but it's very interesting to at least look for it. And I'm thankful that this data is so easily available from AAVSO. I mean, it took me 2 minutes to download the file and plop it into this plot. So it's great. So summarizing, those who managed to build or buy UVEX will not be disappointed. It seems easy to use to me, and I think there are a lot of great science applications, classification of stars, covering the full optical spectrum, and like you can do with any spectrograph, monitoring of variable stars. My favorites for that are BE stars and binaries. And as I've mentioned to Ken recently, I think the best or an ideal setup would be having 2 telescopes, one with UVEX and another with Lhires, so we can still get radial velocities for binaries. So thanks for the invite, Ken. I'll take any questions anybody has.
Okay, well, thank you very much, Drew. That was an excellent presentation. I really enjoyed it and got a lot out of it. One of the things that I would like to ask you is the UVEX allows you to look at more towards the blue, but it also gives you the capability of looking more towards the near infrared. As a professional astronomer, where do you think that an amateur should spend his or her time, more towards the blue or more towards the near infrared?
So the importance of the 2 of those regions, it'll depend from star to star. For certain things, it's very interesting to see the red, particularly the Passion series region. Which, let me go back to that. So for this lower star the star in the lower right, these 3 absorption lines here that are quite huge are the calcium triplet. Those are quite useful features to see for a wide variety of stars. This is actually the range that the Gaia telescope looks at for getting radial velocities for stars. And you can see why, because these features are huge and they're present for most stars. What have found interesting in my own research is that they tend to go into emission, strongly into emission for exotic binaries. So things like HD 215227, which is the only known BE black hole binary. They're strongly emission for that. For these BE SDO binaries where they have a strip subdwarf, those lines tend to go into emission. I don't know exactly why, but it can be a good indicator that the system is some kind of exotic binary. So yeah, it depends, from star to star. I think what I would do if I were to get one of these is probably observe a range of stars of different spectral types, try to get the full optical spectra of all of them, try to stitch that together, and then you would have some idea of what you could expect to see in each wavelength range.
Okay, great. One of the things that I wanted to just point out was that these fantastic spectra that Christian took were largely taken with pretty small telescopes. And it's amazing to me what all can be done with small telescope science. So that's an amazing thing. Let me check and see, Francois, did you have any questions that you wanted to ask?
Oh, hello everybody. No, I have no other questions. That was very, very interesting.
Okay, I do have one final question then here from James Lee, who says, given systems that take thousands of spectra per night, is the role of amateur mostly for high cadence observing?
I would say yes, yes. You know, yeah, professional telescope time is not easy to get. Often very, very difficult depending on what telescope you're talking about. And you all have the unique capability of having your own observatory, being able to do whatever you want. Yeah, I mean, the time series data, like the stuff that Joe has been giving me, is absolutely critical. I could never do that with any telescope I applied for time with, I don't think. So yeah, I think like dense time series is a really critical thing that y'all can do.
All right, great. Well, thank you very much, Drew. We really appreciate having you here, and thank you for taking your busy time to prepare this great presentation.
Thanks for having me.
Next up, we have Francois Cochard, who many of you already know from the first 2 days of this workshop. But Francois is the owner of Shellyak, and I'll let him tell you more about himself, but he's going to give us a presentation on the status of the UVEX in terms of a production commercially available device. So I'll turn it over to Francois.
Thank you, Ken. Thank you very much. And hello to everybody. I'd like just to start by saying that I'm very, very happy to be with you. I'm very impressed, and well, I think I'm more happy than impressed by the number of people coming from all around the world. This is a strange feeling because we were in strange time with the time being, and all of us have a lot of constraints. And by the way, in France right now, we are supposed to stay at home, and I am talking to you from home, but I'm talking to I have the feeling to talk to all the world, and this is very, very great to have you all. And I love this tool that allows us to be in contact with so many people. And really, by doing that in the time being, I think that we are really doing a wonderful astronomy, but we are also doing more than astronomy, because we are keeping links that are so important for all of us. So thank you for the AAVSO to allow us to have this meeting. Thank you, Ken. Thank you, Lindsay, for all the organization. Now, just for kidding, I can share my screen, maybe. Yes, just to follow up to Drew. If you can see my screen, I hope so. Well, tell me, this is where I live, and this picture. So now it's night. The night is here now, but I am not a climber. I'm not climbing. I like mountains. I like hiking, but this is exactly where I live. So this place where there is this guy, it is about 5 minutes from home. So it's just Drew. When you want to come to Grenoble, you will be welcome to see that. And we have great mountains, and we have a lot of climbers all around, and also a lot of paragliders. Well, now let's switch to this presentation regarding the UVEX. No, in fact, I will not switch to the presentation right now. Here is the UVEX prototype. Okay, I hope that you can see it on my screen. This is the most advanced prototype we have today. So we have 2 prototypes at total. And just before switching to the presentation, this is just to show you the instruments. I can quickly change the grating position using the vernier here to show what wavelengths we're observing. I can remove very easily the grating, so the grating can go up to the instrument, and when I put it back in the system, it finds its rotation angle very quickly, and I can put it again in the system. So it's very easy to change the grating, and something that you will never have to do is just I'm opening the box, and really it's important to me that this instrument, you'll never have to do that, because the UVEX never needs to be open. So you can control everything we need by the outside. But anyway, this is what is inside the box, and we are especially very soft moving of the what we call the M2 mirror inside to do the focus of the spectrum. Okay, and it can control from the outside. Okay, so now I switch to the presentation. I hope that you have been able to see properly what I've shown. And now let me. Okay, so let me share my screen with. Yes, it must be okay. Ken, is it okay? You can see it?
Yes, Francois, I can see it fine.
Perfect. Okay, perfect. So I'll continue. So this is really the next generation of instrument for celiac. This is a very important step for us, and I hope that it will be one for all of you. And this is a new step in the spectroscopy, in the amateur spectroscopy, I think, and probably for professionals. So I've shown it for real. When we try to define this instrument, well, by the way, this is something important. Drew explained that the UVEX is so this is a big project launched by Christian Ville, and most of the prototypes so far and all the 3D files are available to print yourself the instrument and make it yourself. The version we are talking about here is the version, the industrial version from Chojnowski. So this is the UVEX by Chojnowski, we call it this way. So it has exactly the same architecture of all the UVEX, but we have made a declination, I would say, of the instrument that gives us high quality instruments. Okay, so it's for me, it's very complementary. So you can have a very high quality instrument. And you can also do your own and put hands-on and do your own UVEX. This is really important to us, and both are complementary. So when we try to define this instrument, I think that this is for sure a new generation, a multi-purpose instrument. We can do a lot of things with it. This is an achromatic spectroscope, and this is dedicated for small telescopes. Well, not only small telescopes, but mainly small telescopes. I'll talk about that later on. We want to, as usual, to get the highest quality or the highest quality results. This is important, so we try to make no compromise, and this was really especially true for this instrument. And well, as Drew told a few minutes ago, I really think it opens new universe to small telescopes, and this is why it's an important step for us. Well, you know that I like to say that the spectroscopy is a triptych between the astrophysics, the instrument, and the practical observation in the field. We'll look at this instrument through these three standpoints, different standpoints, okay? And again, I repeat that this is the optical design have been made by Cambril and the team close to Nice in France that we call the nice people. And so they did a wonderful job, and really, the UVEX is not only an instrument. This is really a project to share our passion and to explore new universes. Okay, so if we look from the science standpoint, I will not go back to what Drew told a few minutes ago, and he's much more competent than I am to do it. But I know that what I understand is that it is important because we will extend the wavelength range from the UV, which is really, we have never been so far with our instrument, up to the near infrared, close to 1000 nanometer. And this is both edges are very new, and of course it also works perfectly in the visible range. Okay, so we can really go from 350 to 950 nanometers. And also this is a low to medium resolution because we can change the grating and we have different grating. And this is important to see that so far we really have some instruments in low resolution and some other in high resolution, like the Lhires, the DHL and so on. And in low resolution, this is more the LP or the LISA. And this is important that we extend a little bit this resolution, and we know that there is some science to do a little bit above a resolution power of 1000. So we can go up to 3, 4, even a little bit more with a higher resolution grating. But the range is roughly from 400 to 4000 for the resolution power. Okay, so these are some examples. All have been made by Christian Buil, and so I love this. I love this image. So the top image is a single shot with a 3 groove per millimeters grating, and you have, if you know that, so we have the far blue here because this is the H and K lines. This is a sun spectrum, of course, and we can go very far in the infrared. By comparison, what we used to have with current instrument like the LP, I don't know if the bottom image is an LP or LISA. This is one of them, I guess, and you can see that we can cover only this part of the spectrum, and then we will double the area that we can cover. So really, this is very impressive. And so this is the same image here with made with a color sensor. So this is really a color camera. This is not a colorized spectrum, but the idea is the same. Just be careful. You have to keep in mind that if we go from 350 nanometers, which is somewhere here outside of the image, up to the 950 or 1000 nanometer, we will have what we call the order overlap. And then, so it means that the second order of the low wavelengths will cover the near infrared. So it's better to have a order filter here. And we have cut at, I don't know exactly, somewhere around 500 or 600 nanometers here, to be sure that we don't have the second order of this part that is covering the other part. And when you look at that, you can see that you have a little bit, you have more contrast in the image. So it's wonderful to have a one-shot image, but keep in mind that it's not totally magic. It's better to have a filter order to split this spectrum. Okay. Well, some results, but again, Drew showed some interesting thing, and I would not be able to talk about science as much as he did. But all what I know is that this spectra has been taken in this case by Olivier Garde with our prototype, and we can go very deep in the blue. And so these are the same spectra taken by Christian Buil, shown by Drew. So I will not spend too much time. By the way, these one have been made by the 3D printed prototype, not by the Chaliak one. But the optic is the same. Okay, so it was from the science standpoint, from the astrophysics standpoint. Now, if we look the instrument from the observer standpoint, what can we see? For me, one important thing is that this is an easy to use instrument. This is very important for us to say that you don't have anymore to open the box. Okay, so to tune the instrument, things like that. Each time that you open the box, you have light leakages and so on. So with the UVEX, you don't have to open the box. You don't need any tool to use it. And this is something light and compact. And it is roughly 1.2 kilograms. So you can see when I fit in hand, this is very small instrument. So it's totally compliant with the small telescopes. Okay, so from the observer standpoint, again, you can change the grating so you can access to different resolution. It is really, this is also very important for us. It is ready for remote operation. So, and we're working currently on a system that will be able to remotely control on one side the focusing of the instrument. So we'll have a stepper motor to control the focusing of the instrument. I hope that you can see it in the image. And we also will have a second stepper motor that will control the angle of the grating. Okay, so again, this is important to be able to do that, because we know that more and more people in the world are using the spectroscopy in remote operation, and so either in the backyard, a few meters from home. So this is my case. I have my telescope a few meters outside of the home, but it can be also at several hundred or thousand of kilometers to put it in great places. So we are ready for that. So it will be an optional module, but we are ready for that. We will use, so if you know the LP, you may recognize here the LP slit here. So in fact, we reuse the LP and the calibration modules for the guiding and the calibration. So the calibration is quite complex, because today, most probably the lamp we have in the calibration module is not enough to cover really the far blue and the far red. But we will work on that, and most probably we'll use a two-step way, which is to calibrate with the a known spectrum. Why not with the solar spectrum, to have the wool dispersion low, and then we'll use the calibration light to recenter this dispersion low. So this is something that we are still working on it. Anyway, we use, if you already have the LP guiding module and the calibration module, you don't have to buy it again, of course. We can access the zero order, and also this is important from the observer standpoint. We will the UVEX will come with the Demetra version, UVEX version of Demetra. Sorry, and we are working on it, and we are starting to work on this. On this software. I continue. Oh, sorry. Yes, here it is. So you have seen that we have a vernier, and you can rotate the index here, and we have some paper that you can replace to when you change the grating. Okay, so you can lock, of course, you can lock the position of the grating to be sure that there is no movement. And at the beginning of the vernier, you have the zero index, okay, to be sure that you can find quickly and easily your spectrum. By the way, this is at the beginning. If you take a small density, low density grating, so like the 150 groove per millimeter or 300 groove per millimeter, the spectrum is very small in this part. So if you put the index here, you will not see anything. So it's important to have some idea of where you are looking at. Okay, well, I've shown that. So here are some dimensions. 130 millimeters in this two direction, 120 in this direction. It is roughly 1.2 kilograms, and we'll have the standard. The UVEX will come in standard with the 600 groove per millimeter grating. Okay, and in option we have the 150, 300. 1,200 and 1,800 groove per millimeters. Okay. Well, now regarding the resolution, it depends. It's always complex too. So, well, what are we talking about? Because the resolution power is very dependent on which wavelengths we are talking about. Well, most of, if you look at on the internet, most of the spectrometers are given at 550 nanometer, because this is the middle of the visible range. But when we are doing astronomical spectroscopy, we more likely talk about the 650 nanometers, because this is close to H alpha. So most of the instruments are given at this position. So this is why we say that we go from 400 to 4,000 as a resolution power. Okay, and by the way, a small notice: in the corner of the table here, you can see that we have not put any figure. In fact, we could put a theoretical figure. Well, by the way, these are theoretical calculation of the resolution, but so far it is very close to what we measure for real. But this is theoretical values. We could have put some theoretical values, but you have to know that in this case, the grating angle of the grating angle position is so inclined that if you use it at this resolution, you'll have a lot of vignetting, because the light beam will be really vigneted due to the angle of the grating. So it's not really serious to use it. So you can use it, but you will lose a lot of light. So this is why we do consider that it's not accessible. Okay, so I already talked about the remote operation of the instrument. It's very important, and I like to say it is important to me also, because I have I have my telescope in the backyard, and for sure I don't want to go outside each time that I have to refocus the instrument or change the grating angle. So I'm working hard to have this option quickly. And I know this is something important for a lot of you. And by the way, we cannot control the grating change. Okay, so as I've shown, this is a very, very manual operation. And well, we tried at the beginning, we tried to do something to have several gratings in a system. But in fact, you know, this is so dense in these parts around the grating. So there is so, when I open the box, maybe you can see it. You cannot see it because there is the grating, but when you have the grating, there is no room close to the grating here. So we tried, but it really, seriously, it cannot work. So we cannot control the grating change, but we can control the grating angle and the focusing. Okay. Regarding the telescopes, so this is well, again, we are still from the user standpoint, for the observer standpoint. The best is to use an f8 Ritchey-Chrétien telescope. Why? The reason is very simple. The Ritchey-Chrétien is a pure mirror telescope. So I mean achromatic. Achromatic means that the focal plane of the telescope is exactly the same for all the wavelengths. Okay, and this is purely achromatic because it is purely made of mirror. A mirror is purely achromatic, and then you can go very deep in blue and red. If you are using another telescope like a Schmidt-Cassegrain or another optics, you will have some glass, and as soon as you have some glass in the light path, you will have some chromatism. And well, it will work, okay? And for some of these telescopes, it's not a big deal, and you can use the telescope you already have. Of course, it will work, but the efficiency will be better if you have a purely mirror telescope. Well, you can also use a pure Cassegrain, but today we have a lot of choice for the Ritchey-Chrétien telescope, and the f8 aperture is very good. There is another architecture, which is the Newton, which is also a purely mirror telescope. And Newton are usually at f5, f4, or even f3.5. In this case, it will work, but be very careful, because if you open the beam with the UVEX, you will increase significantly all the optical aberrations. Okay, so the quality of the image will not be that good. The mirrors are big enough to catch an f5 beam, so you can use the UVEX up to f5. But in this case, you will have a significant decrease of the quality of the spots. Okay, so ideally, if you don't have a telescope and if you want to take the opportunity of getting a UVEX to buy a new telescope, my recommendation is to go to the Ritchey-Chrétien. But as usual, you can also use it on other telescopes, and especially if you already have one, use it on the telescope that you already know. It will be much more efficient. Okay, we can go to a telescope up to 300 millimeters, sorry. and in usual conditions. So I mean, I'm talking about the seeing. So with some normal seeing conditions, not extreme ones. And well, we'll see later the reason for this. It is due to the optical architecture, but of course you can use it on bigger telescopes. And I like, well, I hope that Christian and Olivier Garde are around. They should be present here. And well, Christian says very often, it's important to say that this is dedicated to small instruments, and he is the one who used it, who used the UVEX on a 1 meter telescope in close to Nice a few weeks ago, and he showed that we can do something. But in this case, we can use it on bigger telescopes, of course, and this is very a good opportunity. But you will not have the same efficiency. Okay, so this is what is important is if you use it on small telescope, you'll have a very high efficiency. And by the way, when you said, Ken, a few minutes ago, that it's impressive to see that all the measures that Drew showed and made by Christian are made with small telescopes. This is really a key of this instrument. So if you have a small telescope, you'll have a better efficiency than if you use a big telescope. So you can use it on a big telescope. And as I said, so the attachment to the telescope is made through the LP guiding and calibration modules. So if you are familiar with the LP, and then you just have to attach it. And to show you quickly, I hope that you can see, we have a plate here around the slit that I can remove with the 4 screws, and this plate will be attached to the guiding module, the LP guiding module, and that's it. So, and we'll also have a T-mount thread here if you want to attach it another way. But the usual way, the normal way, is to use the LP guiding module. Okay. Well, I see that there are a lot of questions, but we will come down on that later on. Regarding the camera, what we see today is that thanks to the achromatism of the instrument, we have a quite long available length for the spectrum. And then our recommendation is to use large CMOS sensors, because we are lucky, because the CMOS have usually bigger sensors than the CCD one for a lower price. And then we will use this camera. At the moment, we are not very clear to which camera we will recommend. So if I have to make a decision today, it will be the camera with the IMX 183 sensor. So either the ASI 183 or the QHY with the same sensor. But we'll see, and we know that we will have new cameras to come. For instance, the spectrum I showed you with the 209 was made by Christian by an IMX, an ASI, I think 294 camera color. So and this camera has a CCD or a sensor, sorry, of 19 millimeter long. So it's really wonderful, and the UVEX can do that. So no more, because after that we'll go well, in few words, we will go outside of the lens here, but we can really do it. And by the way, to attach the camera, we just have a ring, an adapter ring. So in this case, this is an Attic horizon camera. Okay, and just have a ring, and I can attach it, and I can tighten 3 screws, managing the rotation of the camera. Okay, again, I hope that you can see it. And so this is the way to attach it, and this is very easy to tune the camera angle. And by the way, it is also compliant with the Attic 460. I know that a lot of you have already this kind of camera. What is important, because you can see it's very visual. if you look at that, we have the cylindrical lens very close to the camera, and this is a high constraint of the UVEX. So we must have the sensor close to this to this part. So we really need to have a short back focus camera. So this is the main constraint we have. Okay, and this is why we recommend this camera, because all these cameras are compliant with this back focus. And by the way, we have already designed the adapters. So the adapters that come to the camera itself. We have designed some adapters for the ATIC, ZW, and QHY cameras. Okay, regarding the slit now, we can use, because we are using the ALPI guiding system, we can use the slit from the ALPI. So we have different widths, and the standard will still be like for all the other instruments, the 23 microns slit. What you have to know is that we are working, we are designing a new camera with a quite different technology. It will be compliant with the ALPI, by the way, but the idea is to have a wider surface, a larger surface, to better cover the full capability of the guiding sensors we have today, especially the IMX 174. Well, today the sensor is bigger than the mirror of the slit itself, so it's a pity. So we will extend that a little bit more, and we'll improve significantly the reflection, because we'll have protected aluminum coating, so with a very good reflection above 90%, where today we have roughly 50% of reflection. So it will be much better to get fainter objects in the guiding sensor. And in fact, the main reason for which we redesign this slit is that we have to go down to extend the IR coating to have a better efficiency at 350 nanometer and 800 nanometer. By the way, I'll talk maybe a little bit later, but I told you that we have no glass, so this is an achromatic system because we have only mirrors inside the instrument. In fact, we have some glass here for the slit, and we have some glass here for the lens, for the cylindrical lens, and we have to make sure that these are very efficient to go down to 350 or even lower with a good efficiency. Okay, and well, sorry, we also propose a fiber connection for the instrument. It can be very useful well, we will use it for tuning the instrument in the manufacturing stage, but this is also something very important for the next generation, because we'll probably use more and more fibers in our instruments. So it is ready for the fiber usage. Okay. Now, so we talked about the astrophysics standpoint. We talked about the user standpoint, the observer standpoint. Now let's talk about technical standpoint. I know that some people in the audience like to talk about techniques. And so this is a Chorny-Turner architecture, which is fully achromatic. Okay, again, I explained that this is, it only uses mirrors. So it's this is what gives the ability to go in the deep blue and deep red. We have really an advanced mechanical design compared to what we did before. And this is really important for me. We have a smooth focusing of the, by moving the M2 mirror, so the secondary mirror, with a very soft system without any tilt when we change the direction of the focusing. So this is a very complex part of the system. And again, we wanted to be ready for the new cameras and telescopes that give really opportunities to go in deep blue and deep red. And so the cameras are doing really improved generations after generation. And now we are ready to catch these improvements. Okay. So Journey Turner architecture, I never know how we can pronounce this, but this Journey Turner architecture is this one. So we use a spherical mirror here and a secondary spherical mirror here, and we have the grating here. So we always have the same architecture. We have a collimator lens, we have an objective lens. We start from the slit or the fiber optics here, and the lights come here, goes to the mirror. The first mirror is collimated, so the outside, the output of this mirror is a parallel beam that goes to the grating. The grating spread out the light, so we still have parallel beams, but with different angle with the wavelengths, and that makes and the secondary mirror makes the reverse, so it refocus the beam to the sensor with different angles. So in this case, we have only one wavelength which is represented, but you have to imagine that the blue one is here and the red one is here, or the reverse. I don't remember. Okay, so this is the idea of this architecture, and so it's wonderful because this is mirror, so they are purely achromatic. But in optics, when you use a mirror like this out of its axis, it gives a lot of optical aberrations. And the idea of this architecture is that, in fact, we have a very symmetric architecture, and in fact we can say in some way that the aberrations of the first mirror are corrected by the symmetry of the secondary mirror. Because of this symmetry, you will correct naturally part of the aberration, not all of them, but part of the aberration. Anyway, you still have a lot of what we call the astigmatism. So it means that the image of a point here is not really a point at the end. This is really a vertical line. And then we have added here a lens, a cylindrical lens. And the mission of this cylindrical lens is to refocus, to reconcentrate all the lights on a few pixels. Okay, so to avoid to have a very wide spectrum, which is spread out across many pixels, and then it will be less efficient on the sensor. So we would have a much higher signal to noise ratio. Okay, so this is the purpose of this lens, to reconcentrate the system. And by the way, you will have to focus also this cylindrical lens on the sensor, and to make sure that you have a very thin spectrum. And again, it will be done, if you can see, it can be done by the outside, because we have small screws accessible from outside to tune precisely this lens. Okay. I think that's it here. So these are some examples of the usage installation of the prototype. The small details, you can see that the camera is not outside of this instrument, but it comes back close to the telescope, and this is much better for the balancing on the instrument, because it will not have too much weight far from the telescope center. So it's a good architecture to save place and weight and so on. Okay, so this is inside of the instrument. So this is the M1 mirror here. So this is really the latest design, and this is the. Yeah,
excuse me, Francois, this is Ken. Yeah. I just wanted to tell you have about 5 minutes.
5 hours, you mean? Okay, I go fast. Okay, I go fast. Thank you. We have something very complex. I mean, complex, the advanced, I would say, to have a very clean movement of the M2 mirror. So when we talk about achromatism, so these are some examples of the spots made by the optical software calculation at different wavelengths, and it shows that whatever is the wavelengths, you have quite the same size of spots, which this is the signature of the achromatism. And just to give you an idea, this is the F8 configuration, and if you open the beam at at the same wavelengths, at in this case at 580 nanometer, if you open the beam, you will see that you will extend the optical aberration. So this is why I told you that it's better to stay at f8, but it will still work at f5. And again, at f5, you will not lose any light. You will have a better optical, less good optical quality, but you will catch all the light. Okay, so this is the inside of the system. I'm going very fast, and just to tell you, when I talk about advanced design, so this is the main part of the instrument, and this is, we have never made a so complex part for an instrument. So this is this part here, the main part, and the advantage of this part is that we attach on one side the telescope and on the other side the camera. So it means that all the camera and the telescope are attached together, and then there is no flexion on the instrument to hold the camera. Okay, and we will have a version of Demetra for UVEX, and we are working on this now. And so we could spend a lot of time on that, but I'm going fast. And the schedule now is that we will launch in few days, few weeks, first run of 10 instruments, and that will be shipped in January. This is planned for January. Next year, and we think that UVEX will be available on stock in May 2021. I hope it will be before, maybe, but for sure at this date it will be available, and we expect the motorization to be available for the second half of 2021. Okay, and that's it. I hope that I've left a few minutes for some questions.
We have a couple of
minutes. Thank you very much,
Francois. So let me ask you the first question from Phil, which was, how big of an issue is the thermal expansion of 3D filament with respect to the performance of the UVEX? And along with this, is there a preferred filament material for making my own UVEX?
Well, I'm not the right guy to answer this question, because I don't have a lot of experience with the 3D printed version, and we did focus on the metallic part. So we personally, I do consider that we need to have a strong instrument with no flexure, and so I did focus on this technology. Now I have no experience, and you better have to ask Christian. Maybe Christian is online, and if you can reply this question. I know this is really a very common question. I cannot answer it.
Okay, that's fine. I received a message from Tony Rhoda saying that he will be addressing that issue in his presentation, which
Perfect.
is coming up in the second group of parallel sessions. So,
and of course, Tony has much more experience in this. Perfect.
yeah.
By the way, I know what I've understood is that the 3D printing has low thermal dilatation, so it's very stable from this standpoint. But in our case, the instrument is quite small, so I think there is not too much problem with the thermal expansion.
Okay, and then I'll ask you one more question, and then we'll need to go to our break and our sponsor presentation. But Valerie wanted to know what order filters are and how they work.
Oh, that's a good point. We have some room. So the order filter are just these are filters that cut the light below a certain wavelength. And for instance, we plan to use a filter order that cuts at 530 nanometer. That means that all the light below this wavelength is cut, and we keep only the value above the 530 nanometer. And by the way, if I hope that you can see this, if I close the sharing, and if you can see it, you have in this system, the slit holder here can be removed, and behind the slit we can add a filter order. Okay.
Okay, thank you very much, Francois. Your presentation was, as always, great and very informative. And as you know, and anybody that knows me knows, I'm very excited about the UVEX. So thank you for doing that. I'm going to suggest that Sebastian go ahead and start our sponsor video now. But before he does that, I want to emphasize to everybody that we have our breakout sessions coming up. If you're going to the Lhires session with Francois, you don't need to do anything at all because that session will be right here where you are. But if you're going to the Star Analyzer or the ALPI session, then you need to take a look at the document that was sent to you by Lindsay during the night, which has the necessary links to go to those 2 breakout sessions. And then after that, we'll have another break, and then we'll have 3 more breakout sessions. And so I just want to emphasize that for the second set, if you're going to the Lisa, then you'll be right here where you are. You don't have to make any changes or go to any different URLs. But if you want to go to the DIY spectrographs with Tony Rhoda or the Echelle with Olivier Garde, then you will need to do the same thing. You'll need to go to that document, find the appropriate URL, and go over to that area. Now, I will be hosting the Star Analyzer breakout session after the sponsor video is done. So for those of you who will be attending that, I'll see you there. Otherwise, I will see you at the end of the day for Woody's presentation, which I think is going to be really good and would be appropriate, just so you know, for anybody who's an experienced spectroscopist and especially anybody who's new, because Woody has a lot of great information about how to organize your observing sessions. So it's going to be filled with good info for all of you. So right now, Sebastian, if you'll start the video.
Great, thanks, Ken. So now we have a special presentation by Dr. Kyu Hong Yoon from CCD, one of our sponsors. He will be talking about CMOS and CCD cameras. So let's see what they have to say.
Hello everyone, my name is Chojnowski and I am CEO of Lhires III. Let me introduce many of the slides in this conference. Quantitative designs the astronomy cameras for almost 20 years, and we support for amateur astronomy camera, also for professional astronomy. We have both CCD camera and CMOS. Now most of our camera is CMOS cameras. Because many CCD sensors is continuous, so now we most of our cameras are CMOS cameras. And I have many questions about how to find the cameras for photometry. In this conference, I'm proud to introduce some of our new CMOS cameras. This camera is Sony XOA76 platform size sensors, and this sensor is 500 bits. Also, there are 16 bits AD converters. Basically, this camera is suitable for photometric usage. There is 24 models of these servers, Flash 600, Flash 200, 68, Flash 411, and Flash 461. I think the most important set of photometric is the mirrors of the system. So we did some tests for these cameras. And this code is the Flash 600. We can say it's very much a linear range from up to 16.5 image counts. And I also test we also test another model which I 411. This is the results. And this result is also very good, which shows the good performance of the mirrors of these cameras. And the whole wheel of this camera is very good, even for the 16, even for 74 microns. The fuel is not very big, but even for this small fuel, they have very much go wheel. For 600, we have measured about 16 days. And for read downloads, this camera is also very good. It's in high gain, you get about 9 years read downloads. And in Louis, you can get 3.5 and for the LED four wheel, the 18 four wheel, you can get 6 image count. The most popular camera of this server is this camera is 4 max. They have this camera at max here. They are probably they have same price cameras. And they get 16 bits, 15 megapixels, sensors. And also this camera is very low access. So even you make every round 600 seconds, you cannot say any match. And also they have no RPI, so they can get of course when we did a special timing error, they become frames, so we have no RPI. The upcoming patch is version 258. This camera is HSG formats. It is associated cheaper than version 600. The version 600 is about 4,000 dollars to 5,000. And then for professional working is 8,000. And this version 268 is maybe more than 2,000 dollars. In this design, we have every special design for the LED for this technology. We have this design to measure the merge. In Sony is only 15K foil, and after gets 18K foil. For project 600, we can some different models, and they should have focus version and they about 7 millimeters focus. And also we have tests like what customer version to reduce the fans the resolution and for the hardware components to reduce things, especially for the RF systems. This is some last features of our user use hundreds. Okay, this is the I want to information. Thank you very much. And I would like to start the AAVSO conference in this year.
Okay, thank you very much to QHY CCD. We really appreciate their support and their sponsorship of this workshop. Without the help of people like them, this workshop would not have been possible. So thank you very much. And with that, I'm going to be leaving this particular meeting session, and I'll see you all in a couple of hours. Take care.
Bye, Ken.
Bye.
Okay, so we continue. Well, maybe we'll give few seconds for everybody to choose their session, and we'll continue. I see that the number of attendees on this session on the Lhires III is going down.
Yes, we had up to 120 participants at times.
Wow,
So,
wow.
Well, yeah, the
Okay.
number is going down right now. Yes.
Yeah. Yes. And then maybe I can start. Well, I'm still waiting for some stabilization of the number of persons here. I don't want that you stay here in this meeting only because it is simpler than staying here instead of changing the link. Anyway, okay. Okay, so I think it's good now. I share my screen. Is it okay? Can you see it?
Yeah, perfect.
Perfect. Okay, wonderful. Well, we have some more time now to talk about the Lhires III. So this is interesting because I just talked about the UVEX instrument, which is the newest one, the one on which we are working today, and which is really which use as much as possible all the experience we have in spectroscopy for some years now. And now we'll talk about the first one that we designed many years ago, and this is I like to say that this instrument is really this is an old friend. In fact, yes, I can switch. So okay, I'm here. So this is really an old friend, and we did start, in fact, the company, Chojnowski company, with this instrument, and so for me this is really this is an important instrument in personally in my life, but I think also for the spectroscopy community. Okay, what we'll talk about in this meeting, and we will talk about this old friend. We'll talk about which observation where we can do with the Lhires III. We look inside of the Lhires III to maybe to better understand its optics and how it works, and maybe it is the opportunity for you to ask questions about the optics. I think this is important that we all understand how it works. It's not very complex, but we have to understand how it works to make sure that we are doing good measurements with them. And again, we look at which telescopes are recommended and for this instrument and which camera. And I will finish with some extension of my thinking, because I think this is more than an instrument. Okay, so this is the Lhires III. Okay, so I guess that most of you know this instrument. It has been designed in fact, the adventure did start in sorry. Here am I. The adventure did start in l'île d'Oléron, Oléron Island in France. It was in 2003. It was for me. It was the first time that I met the professional astronomical community, and I was very impressed at this moment. It was a wonderful meeting, but this one, the kind of meeting that we are having today. So this is really the way to meet people and to see that we can do wonderful things together. And well, I love this image, which is an old image, so taken in 2003. During this meeting, you can see in the middle that there is Christian Buil. Close to him, there is Olivier Tizy, with whom we did found Chojnowski company, and we have some good friends around. So some of them are still in the loop, and some I didn't talk to him for a long time. Anyway, it was an important meeting, and when during what Christian is doing here is he's really putting some first data on the paper, and this data will become the Lhires III. And this book, which is still available at Chojnowski or at EDP editions, it is the proceedings for this meeting. So it's well, this is an old book now, but again, this is important for the community. Okay, so we did create at this meeting. This was also the first time that I met Coralie Niner, who talked about BE stars yesterday, and you know that BE stars is very important in our community because in fact this instrument, the Lhires III, has been designed to propose something to work on the BE star program, and really this instrument was the one which allowed to observe BE star in high resolutions, and it was also the beginning. This is thanks to the instrument that we did create the BES database that Coralie talked about yesterday. So really, it's something important. Now, you know that we can have high and low resolution. So these are very, very, very old pictures. And this is a spectrum of Vega. And you can see that in this case, you have the whole spectrum of Vega with all the Balmer lines, and especially the H alpha lines in this region. And this is a low resolution spectrum, and this is a high resolution spectrum. So the difference is just that we changed the grating in the Lhires III. So today we would have much better results with an LP or even better with a Lhisa for this low resolution instrument, but we can do it with the Lhires III by changing the grating. And you can see the difference of the resolution. In one case, you have a wide range of wavelengths. In the other one, you can see a lot of details in the small parts of the instrument. Okay, and for sure, the Lhires III has been designed has been optimized, in fact, for the high resolution. So as I told you, we can change the grating and then have a lower resolution instrument. And we can even have a low resolution instrument with the 150 groove per millimeter grating. But most of the in fact, the core, the goal of this instrument is really to get high resolution. And high resolution, here are some examples of what we can do within Lhires III. So when we talk about high resolution, it means that for a given line, a given pattern in the spectrum, so it can be either an emission line here or an absorption line here, you can have a lot of details in the profile, okay? And Drew has shown how it is important to have these details. What we have to take, well, by the way, all these pictures have been taken from the web. I even don't know who took them. It was really quickly picked up on the internet. I just Googled Lhires III, and this is what I got. And but they are very representative of what we can get. Now, these two ones at the end, this is interesting because they are they come from BESS and I think RS beam. Well, these are the same, in fact. And this is the QR-Vul star. In both cases, this is the same star, okay? But at this moment, it was in outburst. So the QR-Vul is one of the star, sorry, that has shown several outbursts since the time we observe it as a community. Okay, so this is what you can see with the Lhires III. You can see at one moment you have the star like that, and at another moment you can see it like that. So it's not small details in the spectrum; it's huge and very, very visible. Okay, something important is when you observe in a high resolution, there are two drawbacks compared to the low resolution. So the advantage is clearly that you can see a lot of details in the profile. So you can really analyze what happens in the star. But you have two drawbacks. The first one is that the wavelength coverage is very small. So this is something like 100 angstroms. Okay, so it's very small compared to the whole visible range. So you can see one or two important lines in the same spectrum, but no more. Okay, this is not like in low resolution. And the other drawback of the low resolution, of the high resolution, sorry, is that because you are spreading out the light very much, it means that on each sensor, or on each pixel of the sensor, you will have a very small amount of light, a small number of photons. So it means that to get some good quality signal, so a good signal to noise ratio in your spectrum, you will have to expose for a longer time than in low resolution. And really, the rough idea is that with an LP or Lhisa, so in low resolution, the exposure time is, generally speaking, is something like 1 minute, few minutes, okay? In high resolution with the Lhires III, because of this, the fact that you sent a few photons on each pixel, the exposure time is more usually close to 1 hour or even several hours. Okay, so it means that during one night, you will be able to do much less observations than in low resolution. And then you can see how it is, the two low and high resolution can be complementary. Okay, in the bottom part of the screen here, you can see this is a spectrum of Jupiter. And this is something really incredible because you can see that some of the dark lines are slanted. okay, and some other are vertical. Okay, so this is something wonderful with Jupiter. Jupiter, this is not a star, this is a planet, and then it has a surface that we can observe from Earth. Okay, all the stars are just like a point, but the planets have a diameter, a visible diameter, and if you have enough focal lengths on your telescope, you can really resolve the planet itself. And in fact, you can see that all the vertical lines here are the absorption lines from the atmosphere, so they have no Doppler effect. But all these slanted lines here, and especially the H-alpha line here, which is slanted also, they are slanted because of the rotation of Jupiter, okay, because of the Doppler effect that Stella, for instance, did explain us very well yesterday. Okay, so this is something in this image taken in few seconds on Jupiter, you can really measure the rotational speed of the planet, which is just incredible. Okay, so this is the high resolution advantage. Okay. Sorry. What kind of observation can I do with this system? Sorry, up too fast. I'm here again. Well, this is really this instrument is optimized for high resolution, so you can opportunistically do lower resolution, but it is optimized for the highest grating we have, which is the 204. The 2,400 lines with the slit of 23 microns. And in this case, you will have the highest possible resolution, which is close to, the resolution power is close to 18,000. Okay, so we have other grating modules, and of course, they are very useful and you can do very interesting observations. But I would say that the optical quality of the lower resolution will not be as good as for the high resolution, for a very simple reason that we will see later on, is that we have quite simple optics in the Lhires III. I talked about the UVEX using mirrors, which are purely achromatic because they are just reflecting light. In this case, we have what we call an achromatic doublet, but in fact, it's not really achromatic. So this is a doublet, and then we have some significant chromatism. This is not a big deal in high resolution, because in high resolution, you are just covering a small wavelength range. So in this case, the chromatism is not very important. Okay, again, the chromatism is the fact that the focal plane is different for different wavelengths. But in a small wavelength range, of course, the focal plane movement is very small. So in high resolution, we can do that. But in a low resolution, the quality will not be the same. And then if you use the Lhires III with a 150 line per millimeter grating, then you will have to face some chromatism. And then the quality will not be as good as, for instance, as an LP or a LISA. Okay, so keep in mind that the wavelength coverage is something like 100 angstroms. Well, it depends on the camera, but again, if you increase the camera sensor, you will increase the wavelength coverage, of course, but the quality of the ends will decrease. In fact, so really the good quite small sensor. Well, today we say it's a small sensor, and 10 years ago it was a big one. But if we take, for instance, the ATIC 314, it's really it matches very well with the Lhires III. Okay, so it is really the observation that you can do is very dedicated to bright stars because of this the problem of you will send only few photons on each pixel, and then it is as soon as you go to faint stars, you will not have enough light, or you will have to expose for hours and hours to see something. So, well, by bright star, I mean I know, for instance, that in BESS, I would say that well, I consider that we use small telescopes telescopes, let's say 200, 250 millimeters, 300 millimeters, sometimes above, but when I'm talking about small telescopes, this was a question that you asked some time ago. In small telescopes, I know 200, 250, 300 millimeters, most of the observations that we have in base are up to magnitude 7. Above magnitude 7, you have to expose a very long time. You have to have a big telescopes and so on. So it's really dedicated to quite bright star. Okay, and by bright star I mean magnitude 5, 6, maybe 7. It's more complex to go above. The typical exposure time is roughly 1 hour. Of course, it depends on the magnitude of the target. It depends on the signal donors ratio that you need. It depends on your telescope diameter and so on. So it's really an average, but it is quite long. And then it means that you'll be able to do only few observations per night. Okay, this is only something to keep in mind, and maybe it is very complementary to have a low resolution instrument in parallel to be able to do many observations and maybe to detect some evolutions in the profile and say, and for instance, for the B stars, the low resolution has the advantage to be able to detect an outburst and then to alert other people with a higher resolution instrument to call for observations when we see something moving in a star. Okay, so it's ideal, of course, to observe one line detailed profile, as I showed earlier, and how it changed over the time. So it's perfect for B stars, for cataclysmic, for novae, and so on. And this is also the ideal instrument for Doppler shift measurements. Okay, when we talk about the Doppler effect, well, you have to keep in mind that 1 angstrom of Doppler effect means 50 kilometers per second movement. Okay, so 1 angstrom is not high, and we can really detect a much smaller movement than 1 angstrom with the Lhires III. But in fact, most of the binaries, most of the movement, the proper movement of the star in our galaxy and so on, are visible in this range of Doppler movement. And then with the Lhires III, with the high resolution, you can really see a lot of Doppler effect, including, of course, the detailed profile. If you have an enlargement of a line or a complex profile, this is mainly because of the Doppler effect caused by the star itself. And so really this is the good instrument for Doppler effect. And if you want to do Doppler measurements with low resolution, it means that you will have to observe very fast movement, very, very fast movement, but mainly, most of the time, not binaries and not things like that. Well, by the way, I know that some people have already shown that we can do some planetary rotation measurements with low resolution. I think about David Boyd, who did that a few years ago. But this is, again, when we're talking about Doppler effect, we are talking more probably about high resolution, and the resolution of the Lhires III is perfect for that. Okay. Now let's look at the inside the instrument. I'm looking at the time. We still have some time. You know that every spectroscope works with this principle. We have a light source which is made either by the star itself or by a slit. Most of the time we put a slit to make sure that the light source comes from the instrument and not from the sky, so it's not dependent on the telescope movement. So it comes, we have a light source, let's say the slit. We send the lights to the collimator, so all the light is sent to this collimator. And the collimator, the job of the collimator lens is to collimate the light beam because it is positioned exactly at the focal length of the instrument. So it means that we have a parallel beam at the output of the collimator lens, and then we send it to a dispersion element, which is a prism or a grating. In the case of the Lhires III, this is a grating. In the case of the UVEX also, this is a grating. And at the end, at the output of the dispersion element, we have, again, we have parallel beams, but for the same color, we have parallel beam, but for another color, so for instance, the red beam here has parallel rays here, but for another color or another wavelength, we have also a parallel beam, but with a different angle. Okay, so this is the key of the spectroscope. And then we just have to put an objective lens, which is almost symmetrical to the collimator lens. And then we refocus, because these are parallel beam, then they are refocused on the sensor. But because of the angles, which are different for different wavelengths, then the position of the refocusing on the sensor is different. And then this is what forms the spectrum on the sensor. Okay, so this is the general principle of any spectroscope. And well, by the way, I just showed the UVEX architecture, and in the case of the UVEX, the collimator lens and the objective lens are mirror. Okay, so it means an architecture which is different, so a disposition of the elements which is different, but the principle is exactly the same. Okay, in the case of the Lhires III, we have exactly this system, and the idea of the Lhires III architecture is that this is what we call a litho architecture. And in fact, it comes in the name. So when we are talking about the Lhires, Lhires means litho, high resolution spectroscope. And the litho architecture means that in this principle here, we use the same optic and the same lens for the collimator and for the objective lens. Okay, so it means that we have something like that. We have the telescope beam coming from the telescope, the light coming from the star and the telescope here, which is convergent to the slit. Okay, so the focal plane of the telescope is here. Okay, and then we have the slit, so the light comes through the slit, is sent to a small mirror here, which and then it is reflected towards the collimator lens, which is here in a small holder. Okay, and then in this part you have the parallel beam. Behind that you have the grating. Okay, with a quite important angle to get it is roughly in its nominal position for the H alpha observation. Okay, and in this case, this is a reflecting grating. This is the same for the UVEX, by the way. And it means that so then the light is sending to the grating, and it is sent back because this is a reflecting grating. In this case, you have the blue and red rays that goes out with different angles, but again, both parallel until the objective lens. So in this case, it goes a second time through the same optics, and it is sent to the sensor. Okay, and by the way, you see that if all these optical schematic were in a plane, in a very old symmetric, then the light here would be sent again to the sky by the mirror. Okay, but in fact, this is not the case, because we have a kind of 3D schematic of the system, because this flat mirror here that sends the light coming from the slit towards the grating, it has a small angle that makes that, in fact, when the light comes back from the grating and through the collimator lens, it doesn't have exactly the same position, and it goes just beside this flat mirror, okay, towards the sensor. And by the way, this is that makes that in the Lhires III, the lines are slightly bended. Okay, so the bending of the line is normal, and this is really due to this the phenomenon that we have a 3D optical schematic. Okay. We can, oops, here am I? I told you that we have a very limited, in this case, this is not a, this is a low resolution spectrum, and but we have with the Lhires we can look at a very limited area of the spectrum, okay, and in fact it is even smaller than that, than what is represented here. But the advantage of the Lhires is that you can rotate. If I go back here, you can use the micrometer here. It will rotate, and then it will push on this part of the grating, and then it will allow to change the angle of the grating. Okay, and by changing the angle of the grating, we will change the wavelength range that we are looking at. Okay, so by rotating the micrometer, we will choose at which position we want to observe in the visual spectrum. Okay, in the visible spectrum. Well, I know that most of the observations are made close to the H-alpha line, because H-alpha is probably the first line to observe in any star. But well, maybe we should, as an amateur community, I know that we should observe more often outside of the H-alpha line. Anyway, observing H-alpha with the Lhires III is quite easy, because we have a lot of calibration lines and so on. So there are good reasons to observe in this area. But if we change the grating angle by the micrometer, we will change the bandwidth we will observe in the visible range. Okay. Something else which is important, I think. We do have inside the Lhires III, we do have a guiding module which is included, which is embedded in the Lhires III. If I look at the, well, I will show you again. The idea of the guiding is this one. Well, sorry, the texts are in French, but the graphic is useful, I think. When you have the light coming from the star here with dark lines, with the black lines, it goes directly to the slit, and then the light goes through the slit, and then it is sent to the spectroscope, which is in this part. So you'll have the collimator and so on. Okay, so when you have a star exactly on the axis of the telescope, it will go to the slit, and then the light will be spread out by the spectroscope. But if you have a small angle, so if you look at an older star in the field of view of the telescope with a different small distance and angle distance from the star you observe, then the light will be sent to this part, and this is a mirror here. Okay, and in this case, you will send the light here. It will not go to the spectroscope, but it will be reflected down to this secondary mirror and sent to what we call the guiding optics. Okay, and this system will make that the CCD here, the guiding camera, or CCD or CMOS now, but the guiding camera, which is here, will see exactly the telescope field of view, except that in the middle here, we will see a dark line, which is in fact the image of the slit. Okay, so as a result, if we look at what we'll see is that if you look at the guiding image, you will see the field of view of your telescope with a few stars. Okay, and you will see, well, a dark line inside the image. And by the way, dark line in the image, when we observe during the night, all the image is dark. So you will see a dark line in a dark image. So it means that we'll see nothing. But really the slit is here. And if you put, by moving the telescope, if you put any of these stars in the middle of the slit, then you will see in the acquisition image the spectrum. Okay, and if you have a polluted sky, if you are observing in city center or in a polluted environment, then you will also catch all the spectrum of the sky background, and you can see it in your spectrum. Okay, so you are sure that outside of the slit you will be perfectly dark. So here you only have the noise from the, not the noise, but the signal demos and the dark signal from the camera. But here you also have the light pollution, and here you have the spectrum of your star. Okay, so this is the principle of the guiding system. And if I come back to one of the previous slides here, we exactly have the same system. So the slit is here in the Lhires III, okay, and if the light doesn't go to the slit, through the slit, then it will be sent back to this guiding mirror and sent to this. We have an optics inside, and we will put the CCD. So the guiding camera, again, it can be a CCD or a CMOS camera. And now most of the time it is CMOS camera for the guiding. And in this case, the image is sent back to the guiding camera. And this is this camera which allow to track the star image in the slit and make sure that we put as much light as possible in the slit. So I was happy to hear yesterday that Lorraine told us that she heard that what is important during one observation is to put as much light as possible in the slit. Really, this is the key of a good observation, and this guiding system is made to do the job properly. Okay. Well, I continue. I don't know if there is a lot of questions. Tell me. Well, not too much at this moment, I think. I will see at the end. Anyway, we'll keep the question for the end, and you can ask if you want. I was here. Something which is also important. When we look at the telescope that the optimal telescope for the Lhires III, in fact, the Lhires III is a F10 design. What means F10? It means that the focal divided by the diameter is 10. Okay, so F10 it is what we call a slow telescope. Okay, and it is we most of the time we would prefer to have a faster telescope with a smaller F ratio. But the point is that, well, by the way, F10 is typically what we have with the Schmidt-Cassegrain telescope. Most of the Schmidt-Cassegrain telescope are F10, and then they are perfect for the Lhires III. And by the way, we can go down to F8 without too much problems. If I look again, if I come back to this, the F10 comes from the fact that you see the diameter of the collimator lens here. If we would have, imagine that we have a wider cone here, and we have a F5, for instance, cone, then the cone will be bigger here, and we would have some vignetting here on the mirror, okay, because it will go, the light would go outside of the mirror, and even more here, we would have some vignetting at the collimator position. If we want to have a wider aperture, a faster telescope, and with the F6, F5, F4, it means that we would need to have a bigger collimator here. And bigger collimator means much more expensive. We would have to have a bigger grating and so on. So all would be would have more weight, more heavy, or will be much more expensive, because when you extend the diameter or the size of the optical components, the price increase very fast, and so on. So it is very complex, and this is the reason. And we would also have much higher optical aberrations. So this basic optics would not be enough anymore. So this is where come the F10 constraint from for the Lhires III. Okay, and now you really have to understand that if you put it on a bigger telescope, I mean, an F5 telescope, if you put, for instance, the Lhires III on a Newtonian telescope, in this case, which is most of time F4 or F5, in this case, what happens is that part of the light is not going through the spectroscope. So in fact, you will have a good result because the spectrum will be good, will be perfect, but you would have exactly the same result with a smaller telescope. Okay, so you are not taking the advantage of your diameter, okay, in this case. And well, you can say, okay, but in this case, we just have to put a Barlow lens in such a way that behind my, for instance, my Newtonian telescope, I can extend the focal length and then have a faster telescope. That is true, but in this case, the result that makes that if you extend the focal length of your telescope, in this case, you will increase the image of the star in the focal plane of the telescope. Okay, so you have to keep in mind that the size image, the star image size in the focal planes depends on two parameters, which is the seeing. Okay, so the extension of the angular size of the star in the sky because of the turbulence of the sky, and the second parameter is the focal length. So if you double the focal length, you will double the star image size in the focal plane, and for a given slit, then you will lose some light in this case. So you will not lose the light this way, but at the end, you will lose the light because not all the photons from the star will go inside the slit. Okay, and so in this case, you can tell me, okay, but I just have to increase the size of the slit. You are right, but if you increase the size of the slit, in this case, you will reduce the resolution. Okay, because when you have also to understand that a spectrum, the 2D image of the spectrum, is a multiple image of the slit at different wavelengths. Okay, and if I have a very thin slit, then the image, the lines will be very sharp. And if I have two emission or absorption lines very close from one to the other, in this case, if my slit is small, then I will be able to detect the two lines. But if my slit is wider, in this case, I will mix all the information from the star and I will see only one line in emission or in absorption. Okay, so you can extend that, and you can open the slit, and we have different slits of 35, 50 microns, and people use it, and because it's very useful. But you just have to know that in this case, you will decrease the resolution of your instrument. Okay, so this is why we say that, in fact, we can use the Lhires, or this is exactly the same for the UVEX that I told before. You can use it for small telescopes, and if you are using it on bigger telescope, of course you will catch more light, but you will have to choose between the resolution. So, and if you want to have the highest resolution, because you want to see a lot of details in your light profile, in this case, you will have to keep the small slit, or the 23 micron slit, or even lower. Why not? We can have even lower, smaller slits with the new CMOS sensors, because the pixels are smaller. And then we can even have smaller slits to have a higher resolution, but at the cost of, at the expense of losing light at the input. Or if you want to go for faint targets, you can open the slit. And in this case, you will take the advantage of your bigger diameter, telescope diameter, but you will lose resolution. Okay. Well, I hope it is clear. The next one is regarding the camera. In this case, we have much less constraints than the UVEX. I told you on the UVEX that the camera has to be very close to the grating and to the cylindrical lens, and this is very dense in this part, so it's not easy to put some parts to attach the camera. This is not the case for the Lhires III. For instance, if I look at if I go back to this schematic, you can see that we have some room here between the camera adapter here and the sensor. Okay, so here we have even put some constraints when we design the Lhires III. We wanted to be able to attach a DSLR camera, and the DSLR camera has a distance between the sensor and the plate here, which is the reference. So I hope that you can see my mouse. I can see the distance here, sorry, is close to 55 millimeter, which is huge, in fact. Okay, and I can even tell you that it was really a challenge. So because this is because of this distance, we wanted to have the 55 millimeters here, and then we designed the instruments in such a way that the beam goes very close to the structure of the chassis here. This is why, for instance, we have this angle here, because we have to attach this part, and this is really to make this beam as close as possible from this part of the chassis, to save some space here and to have enough back focus for the camera. Okay. Well, we don't need to have a large chip. Well, I don't remember exactly.
Hey, Francois,
yes.
we're seeing your multiple slide view as opposed to full screen.
Oh, and so it means.
Yeah, just try sharing your screen again.
Okay, maybe. Can you see?
Yeah, there you go.
So you see the slide for the cameras, or?
Yes, so I see the slide that's has camera up at the top. No strong constraint on the model.
Perfect. Yep. Thank you very much. Thank you.
Yep. Mm-hmm.
And then thank you for alerting me. We don't have a lot of content, as I said. For the UVEX, I told you that we can have a long sensor, 20 millimeter sensor, which is very long compared to what we need for the Lhires III. Again, we have with the Lhires III, I don't remember exactly, but this is something like, I would say 10 millimeter or even 9 millimeter. I don't remember exactly. So if you use a larger sensor, of course the spectrum will be longer, but again the camera at the edges will be not the same quality. So in this case, there is no need, in fact. So if you have a big camera, you can use it, and you'll have a larger spectrum. But if you don't have one, a small camera is enough. And the same for the pixel. The pixel size, we have a 23 microns slit, and then we can really use any camera with the pixels from 4 to 9 microns. So well, today it means that almost all camera can fit. We have really no constraints. The point again, if I come back to to the same system. Here is that there is something important to understand also. In this architecture, we use the same optics for the collimator and for the objective lens. So it means that this lens must be focused at the same time on the slit. Okay, so it means that the distance plus the distance here must be exactly the focal length of the lens. Okay, and at the same time, this lens must be also focused on the CCD. So it means that the CCD must be exactly at the same position of the slit. So the distance here must be exactly the same distance here. So we have a constraint here. We can take any kind of back focus on the camera, but at the end, the sensor must be exactly at the right position. And here we have a strong constraint. And for this reason, we have a lot of different rings, adapter rings with different lengths to adapt to any camera that you can have. So we can cover almost all the cameras, but depending on your camera, you may have to change, to select, or we have to choose the right adapter to make sure that we have these constraints. Okay. Okay, now I think that this is I would say that we have a tolerance of the nominal position plus or minus 2 millimeter. So the CCD plane must be at the nominal position with the tolerance of plus or minus 1 ideally, but we can go up to plus or minus 2. And if we don't have that, then the spectroscope will not work in good condition. So you will be able to do the focusing of the instrument by rotating the focal length, the collimator lens, sorry. This is the way to focus the spectrum and to have the sharpest possible spectrum. But in this case, if you don't respect this distance, the result is that you will never be able to go to the nominal resolution of 80,000. Okay, so it will be even at the best focus position, the width will be a little bit too high. Okay, I've almost finished. What I want to say now is, so we talked about the instrument, but for me, the Lhires III is really much more than an instrument, because, well, of course, we have now a lot of users all around the world, and this is something for me fascinating, and this is very impressive. And we have a lot of people. I'm sure that when we are talking right now, somebody in the world is using a Lhires III, and this is not only an instrument, but this instrument helped us, made that we built a community around this instrument, and this was very a wonderful tool for years to build the community and to work all together. This is something very impressive. By the way, this instrument has made a lot of publications. There is a lot of papers, scientific papers, even in the best scientific journals, like the Astrophysical Journal, the ANA, Astronomy and Astrophysics, and things like that. Yesterday, for instance, I just sent a request to the ADS. You know that the ADS is the database where all the astronomical and astrophysics papers are stored and recorded and annexed. And I've just looked for Lhires requested all the papers with Lhires, and we have exactly 100 yesterday, maybe 101 or two today, I don't know, but yesterday it was exactly 100 papers in the ADS. So it means that this instrument has been used by many observers, and a lot of them, of this observation, has been used to do real science, and most of them are made by amateur astronomers. So it means that it allowed amateur and professionals to work together. So we never imagined that at the beginning when we design and launch this instrument. But this is something impressive. And also I've written here the roughly, well, I didn't count for sure. Maybe this figure is wrong, but I estimate that roughly 60% of the H-alpha observations in BESS, because we, generally speaking, we prefer to have high resolution spectra in BESS. And I would say that 60% of the spectra are made with the Lhires III. Okay, so and it has also been a standard for the software development, and thanks to this instrument, we have been able to build the best program and the best database, and through the best database, we define a standard for the fixed file format and so on. So this is a copy of the request I made on the ADS yesterday. Okay, so for me, the Lhires III has not only opened the spectroscopy to the amateur community, it has also offered new opportunities for amateurs and professional astronomers to work together. So this is something, well, without the Lhires III, we wouldn't be here all together today to attend to this, to the current meeting we have today. And this is something just incredible. And this adventure still continues, and we have even the more people are involved in the spectroscopy, the more wonderful program we will do together. And really, we are all different, and when we all work together, we are doing things that are really incredible. And thank you for that. And well, let's continue and let's work together, and let's continue to have fun and science, as Ken said yesterday. Okay, so I think I've finished. I don't know if there are, what time is it? Oh, it's almost time. Perfect. And so now I think that's depending on how the other groups will join. Maybe I can look at the number of attendees here, but maybe people will join us again. But if you have few questions, you can ask. And by the way, I will look at the questions.
We haven't got any questions so far, so people, come on.
There's one question in here from Nancy Morrison. How's the wavelength calibration done? Is it a lamp, night sky, objects?
Perfect, thank you. I didn't talk about that. Of course, there is a calibration lamp now inside the, I go back. Now we can, well, I can go to the initial picture. We have a calibration lamp inside the system here. I cannot see it on the picture, but we have two buttons. One is for the flat lamp and one is for the calibration lamp. And the lamp, we have an argon and neon lamp. And again, when we are observing close to H-alpha, this is very great because we have a lot of neon lines that are very easy to calibrate. So the calibration lamp and flat lamps are now integrated inside the Lhires III. At the beginning, it was very manual. So we had a button here to rotate the small neon lamp in front of the slits, but now we have something which is motorized, and then we can control it remotely. And this is just automatic. So we have an internal calibration lamp.
There's another question. If the grading needs to be, or from a Eurosemestric, if the grading needs to be replaced, what is the physical size of the grading?
Or the grading we have in the Lhires III are, for the high resolution, this is 50 per 25 millimeters, and the thickness is 9 millimeters. And which is a standard grading from the industry. And for the lower resolution, if I remember the up to the 600 line per millimeter, this is a 25 per 25 millimeters. And the reason is that for the high resolution, we have a wide important angle inclination angle, and then we to cover the full beam, we have to have a long grating. For the smaller resolution, the 25/25 is enough because of this angle. I hope I'm clear.
And one last question. Does the UVEX have an auto guider?
So the UVEX doesn't have, well, really the guiding and the calibration module is included in the Lhires III. It is not included in the UVEX, but in the UVEX we reuse the LP and guiding and calibration modules. So you know the LP, and the LP we have the spectroscope, we have the guiding module, and we have the calibration modules. The two guiding and calibration modules can be reused for the UVEX. So this is why we decided not to make the guiding inside, because we already have some great tool to do it.
Okay, I think that's, let's see. We'll probably do this one last question before I think there's a break as people can move to the next session. But this
absolutely.
one says,
absolutely. What time is it? Yes, we can stop for well, less than 10 minutes.
Yeah.
And maybe well, we can stop here, and I can also, well, I see some questions. I will reply as much as I can by written replies. Okay, so we stop here. Thank you very much for your participation, and we come back in less than 10 minutes from now. In this on this channel, on this session, we will talk about the LISA with Olivier Garde. Okay.
Cool.
Thank you.
Thank you so much.
Okay, so we're on time. So if you want to continue, Francois.
Okay, so this is now the place for Olivier Garde. Okay. Well, by the way, I don't have any more control, I think. So maybe I hope Olivier you are around. Yes, I can see you, Olivier. Perfect. And Olivier, you will now talk about the LISA spectroscope. And Olivier, you are an amateur astronomer for a long time. You have a lot of instruments. You are deeply involved in spectroscopy for many years. Also, you have made wonderful observations. We know each other for a long time. And by the way, you work for Chojnowski as a technical consultant. So we also work closely every day. And now I'll let you talk about the LISA. Thank you very much. And again, I keep an eye on the questions if necessary, and I will interrupt you if there is something urgent. And if not, we will take the questions at the end. Okay? Is that okay, Olivier?
Okay. Thank you, Francois. Hello, everyone. So this presentation, I will present you the LISA spectrograph. So first, so LISA, what does it mean? The name mean? So it's a long slit intermediate resolution spectrograph for astronomy. And here is some detail about the LISA. It's a very sensitive spectroscope dedicated to low resolution. The resolving power is typical 1000 with a 23 micron slit, but you can have more or less depending of the slit width you use. But we go further to understand what it means. Inside the LISA, we have 1300 growth per millimeter rating, blazed at 500 nanometers. And the typical spectral range is around 400 to 75 nanometers. But Chojnowski also near infrared version will go up to 1 micron wavelength. This is a typical spectrograph dedicated for a very faint target. We will see after which kind of target we can do with this spectrograph. The LISA have Argonian calibration module. It's very useful to calibrate easily the spectrum. And you have, of course, a large choice of slit. First, the LISA spectroscope on the optical instrument. You can use your LISA with several telescopes. The only thing you have to think it's about the FD ratio. The FD ratio must be close to 5 for a good efficiency. That not means that you can, of course, use LISA with FD8 telescope, but with less efficiency. So you can, for example, you can take Vega. You can see you can't see difference between FD10 or FD5 with a LISA because the time exposure is around 1 second or less. But for very faint targets, it is difficult to do a spectrum with FD10 ratio. So in this case, you must use a focal reducer to go down to something close to 5. And you have to use 2 cameras. First, the spectral camera to take the spectrum. We recommend the ATIC 414X because it's very sensitive with a large pixel around 6.45, I think, micron. So it's they are big, big pixel size, and it's very efficient when you do a very, very low spectrum. And for auto guiding, you have the choice. You can use, in fact, the choice of the guiding camera depends of your setup. If you have a setup with low focal length ratio, you can use the IC120. It's good. It's a good camera for this. But you can also, if you have bigger focal, you can use IC174 or QH174. Or if you have an older model, the ATIC 314L Plus, it's good also for guiding with a laser. The laser spectroscope, there are the laser body, the black part, and you can add on the main body the calibration module. You see on the picture, it's the white module with two switches, one for the tungsten lamp, the other for the calibration lamp, the neon argon lamp. And you have to put two cameras, so the auto guiding camera in blue and the spectral camera in red. And you mount all this setup on your telescope by a ring adapter. Here there are 2-inch classical 2-inch in diameter to put in an eyepiece. But for SCT telescope, you can use a special ring that you can fit directly the laser on C14 or C8 or for the Smith-Cassegrain telescope. If you look inside the laser, what we can see, we have several parts. So we have, of course, the telescope mount, 2-inch, but inside the first thing we have, it's a reflecting slit. And you have also a mirror on the bottom, and the collimator, and a grating, and a lens, objective lens for the output of the spectrum. We have also an optical for the guiding, for the guarding part. And you have a hole inside the laser for the calibration window. In fact, it's a simple hole. When you put the calibration module on the laser, this small hole shows the light coming from the calibration module. The optical diagram. So, in fact, the incoming light beam coming from the telescope go through the slit. The slit is here. I think you can see my my cursor here. And the light beam cross the slit and go down to the small mirror here, who turn the light beam into the collimator. The collimator is here. And the collimator make the beam parallel to go through the grating. The grating is here. And after, there's the grating disperses the light. So now we have a spectrum. And the spectrum goes through another lens, here, the objective lens, to focus the spectrum on the sensor, output of your CCD here. On the optical diagram for the auto guiding is more simple. The incoming beam always the same. Go on the slit, and the slit is a reflecting slit. So you have a small mirror here, who the auto guiding camera see the slit, and you have an image on the right show the slit in black, the black line, and here it's a ring nebula, and you see that the reflecting slit show exactly what the telescope see. Apart, it's very important with LISA, but also with the Lhires III or other spectrograph, is that you must respect the back focus of different parts. The first back focus is between your telescope and the slit. It's 41 millimeter. That means you must have enough place, enough back focus on your telescope to have to reach the 41 millimeter necessary to have to focus a star on the slit. And the second main back focus is back focus for your camera, for the spectral camera. You need to have 54.85 millimeter from the part of the side of the LISA on the sensor plan of your CCD. It's very important to not exactly have exactly the same back focus, but you have to be close to this value, because if you don't have this value, you lose many resolution of your spectrograph. And of course, you have the same problem with guiding camera. You must have 17.5 millimeter from the side of the ring of the auto-guiding port to the focus plan of your guiding camera. Here is a picture of the LISA set up on your telescope. So here we have an ATIC 314L plus for auto-guiding, and we have for the spectral CCD an ATIC 414RX camera. You have, so we saw the calibration module with the two switch for the halogen lamp and for the argon neon lamp. On the argon neon lamp, here is the spectrum of argon neon lamp taken with the laser. So we see on this graph that you have neon lamp mainly on the red part of the spectrum. On argon neon lamp, we go down to 4,000 angstrom. That's very useful to well calibrate the spectrum, even in the blue or in the red part of the spectrum. LISA comes from a standard slit. For slit, in fact, the slit have 4 positions. It's very easy to change it. You have only to unscrew two screws to maintain the little part of the slit. On the slit have 4 positions. On to change slit width, you only have to turn the slit in the right position you need. There are 3 models for the slit. One is coming with laser. It's a 15, 19, 23, and 35 micron. And you can have, you can buy also other slits. One with 19, 50, or 75 on 100 micron weight, and also a photochrometric slit with this value of width. Alors, you must adapt the width of the slit depending of manufacturer. They are not a universal width for the slit. It depends of what you want to do on which telescope you use the laser. You can use a wider slit to increase the incoming light, but if you increase the wider of the slit, you decrease the resolution. It's a choice. You can use a larger slit with large diameter telescope. because with a large diameter telescope, you have a bigger focal length. So you need to have also a bigger width slit. For example, with a C8 or a Richter-Chrétien 8-inch or a Newton telescope of 200 millimeter in diameter, you need 23 micron slits. But with bigger telescope like a C14, the Richter-Chrétien of say 16 inch or a Cassegrain telescope of 400 millimeter in diameter, you need a 35 micron slit. And with a bigger telescope, of course, you have to increase the slit width. And typically, on a 1 meter telescope, you use a 50 micron slit. But in other case, you can use a narrow slit to increase resolution. For example, if you take the 15 micron slit, you can go up to 1000 resolution, maybe 1200 in maximum, to increase the resolution of the LISA. The photometric slit, I just take a few seconds to explain why we have this kind of slit. This slit is very useful for absolute flux calibration. In fact, on the same size, of the slit, you have two different width slits. One is for photometry, and the other is for spectra. So you put, in fact, for photometry, the target into the larger slit, and to take the spectrum without any change, you can take a spectrum with a narrow slit nearly at the 10 times without to change the slit during the night. So I have tested the LISA on several very different telescopes. Of course, you can use the LISA with 200 in diameter telescope, or maybe less, or Matsyukov 100 millimeter in diameter. But here that the typical instrument when I use my LISA on. First, this is a C14. You can see here the LISA setup on a C14 with a focal reducer, because the C14, the FD ratio is nominal at f11. So we need to have a beam close to FD5. So we need to use a focal reducer to use the LISA on the C14. Another setup on a bigger telescope, it's a Richter-Chrétien of about 500 millimeter in diameter, 20 inch. So the same thing, we must have a focal reducer to this Richter-Chrétien. It's close to FD8, so you need to have FD5. So I use here, we can see it because it's the noise piece. We have a focal reducer from Astrophysics, CCD T67, to have a FD ratio close to 5. Another one, another Richter-Chrétien of 600 millimeter, 24 inch. The same problem, you have to use a focal reducer. On a bigger telescope, we use it on a 1 meter telescope, also with a focal reducer. And here is my setup. I usually use at home. So I have a Richter-Chrétien of 400 millimeter in diameter. This is an AstroSib, a Russian telescope. So we will see my setup. And I have two spectroscopes. I work with two spectroscopes at home. One is a fiber spectroscope with an e-shell spectrograph. And the second is the Lisa, or low resolution spectroscope. And I just push the button on the right here, on the left of the telescope to switch from one setup to another. So processing Lisa spectra, how we can do. Here is a raw spectrum of 900 second exposure. On this raw spectrum, I just remove the hot pixel present in this image just to show you how I can process Lisa spectrum. So you can see some emission line on the profile here. And this is the binding area I use to process my spectra. Typically, it's a spectra from planetary nebula. With you can see here we have H alpha, and close to H alpha we have the nitrogen line, the forbidden line of nitrogen. And here you have the two line of forbidden line of oxygen. On center here you have the H beta line here. So you have also the line who cross all the slit is the atmospheric or thermic line or pollution line that we have to remove from the spectrum during the process. So during the reduction process, we do a subtraction of the background sky. The background sky area are in blue, the rectangle in blue. And for processing my spectra, I use both software, ISIS or Demetra. It depends the day. I use these two software. But you can also use other software like SPCODS, Visual Spec, BAS, or if you are very familiar with Python, you can also use Python to reduce your spectrum with Lisa, with the Lisa spectrum. Which kind of target we can do with Lisa? So we can do everything. We have very faint targets. So faint BS star, symbiotic stars, novae, PN candidate, or planetary nebula, or very, very faint nebula, supernova, galaxy with high redshift, quasar, comets, or more generally, low light target. I insist, but the Lisa, it's the spectrograph dedicated to very, very faint target. So here is an example with the comet C 2019 year 4. With this comet, we can see the I take this spectrum in April 2020, so this year. And you see on the left the auto-Gatling field with the comet. It's very faint. Huh? I take exposure about 10 seconds on the auto-Gatling camera to have the comet. You can see the slit, the black line. And I put the comet into the center of the slit. And I obtain the spectrum you see on the right of the picture. I take 9 exposure of 600 seconds each. And I try to identify some emission line that we can see on the spectrum. Other target, a quasar. This is a quasar up to magnitude 16.5. So it's a very faint target. Here is, you can see on the auto-guiding field, you can see the target. It's very faint. So I put also the target into the slit. But because the target is very, very faint, I auto-guide on nearby star. So I think I have auto-guiding on this star for auto-guiding. And I just checked that during the auto-guiding, the target was always at the same place in the slit. So here is the result. The large emission line you see here, it's in fact the Lyman alpha line that at hydrogen line. The rest line is in the far UV at rest, but with the big, very big redshift of this quasar, you can see in the visible domain. So the line, it's around 5,400 angstrom because of this very high redshift. You can also do imaging with a laser. It's relatively simple. You, for example, if you want to scan this ring nebula, you put the edge of the target into the slit. You auto-guiding on a star close to the target. So on the auto-guiding field, you can see the star for auto-guiding. And you take, for example, for exposure of 100 seconds each. And after this first series, you move your auto-guiding side point by 3 pixels in the Y-axis, and you take another 4 exposure, and so on, to, in fact, to scan all the planetary nebula. And with ISIS software, you have a special command. I watch on the screen. And for more detail how to obtain this image, you have the link of the Christian Buell page. We explain how to do imaging, spectral imaging with a laser. And we obtain this kind of images with forbidden sulfur line, H-alpha line, forbidden oxygen line. And when we combine all these three pictures, we obtain a color picture of this ring nebula, but without any star in this picture, just the nebula. Another thing we can do with ELISA, very simple. I just take, this is the Horsehead Nebula, and I just take a single exposure of 300 seconds. And because I have all the Horsehead on the slit, and I have also the sky around the Horsehead Nebula, so I have 2 different spectra at the same time. So the area 1 that I call area 1 was inside the Horsehead. You can see the result on the left, on the right of the spectrum. And this spectrum is very different from the spectrum from the outside area of the Horsehead. You can see, for example, outside of the Horsehead Nebula, you have lose the H beta line, was not present on the outside of the Horsehead Nebula. So it is very simple to do it with ELISA. Another target, a Cepheid galaxy, magnitude 15. I only take 3 exposure of 20 minutes each to have this spectrum. And you will see that, for example, the H alpha line is not at the rest line about 6,062 angstrom, but close to 7,000 angstrom. So redshift and redshift, not a very, very important redshift, but a sufficient redshift. That means that the Cepheid galaxy, it's quite long. Another target, this is a planetary nebula confirmation. So this is a typical target who need to have a spectrum to have the signature to prove that this is a planetary nebula. And we take this spectrum with a 1 meter telescope at Calern Observatory. It's near Nice of the French Riviera. Here is just for 1 hour exposure, for exposure of 15 minutes each. Another target is a supernova in in the galaxy M101 in 2011. So for this spectrum, I turn, in fact, my Lisa to have at the same time the supernova and the small NGC 5455 at the same time in the slit. So I just turn the Lisa to have the right rotation of the slit to have these two targets at the same time in the slit. And with only 6 exposure, we have two spectra. The spectra from the supernova and the spectra from NGC for 5455. Another target, very faint BA stars in the Cygnus, about magnitude 15. This target is very far in our galaxy. So you can see the continuum is reverse for classical BA star. That's because the continuum is going red because there are many interstellar particles between the target and us. Sometimes we have a very strange object like this spectrum. We can see some emission line, but these lines are not at the right place. And the target, IPP1, is not a well-known target. It's a new object discovered by amateur. So with this line, we can check that, in fact, the lines are shifted in the red. KN66, it's a planetary nebula, a classical planetary nebula, so a target in our galaxy. And we can see that IPP1 have the same emission line, but redshift in the red. So it's a target with not, this target, IPP1, is not a target in our galaxy. And we can calculate by Doppler effect the redshift Z by this formula on the right for each emission line we can see in our pulse spectrum. So lambda 0, it's a value of the rest line, and lambda 1, it's the value of the measured line on our spectrum. And we do the average of each line, and we find this redshift. And with this redshift, we can calculate also the leak velocity and the distance of this new object. This is a galaxy. And with the Lisa, with my team, we have discovered about 4 new galaxies. with you can see two of the 4 galaxy, 2 spectra of the 4 galaxy, which different redshift. And we have published our result in article, and you can download this article on archive.org website. You have the link on the screen. For more information about the LISA spectroscope, you can also go to the Celiac Instrument website, and you can see, you can discover the LISA for the visible domain, the LISA for the near infrared domain, all accessory we can be fitted on the LISA spectrograph. So thank you for your attention, and if you have any question, feel free to ask a question.
Okay, Olivier, thank you very much. Well, I see 2 questions that just arrived. Olivier, from Stephen Lowe, having 2 stars in the slit with the LISA, how do you separate?
Oh, it's not very difficult. If I come back to for example, you have this kind of raw spectrum. You can see we have many stars or many targets in the slit at the same time. We have the planetary nebula with this emission line here, but we have another star here, just close to the PN, and we have another star here and another star here. So it's not difficult. You process first. You first process, for example, this target, but after you can process this target and this target. All target in the slit, you can process all target present in the slit at the same time. So it's not very difficult to have many targets in the same at the same time in a raw picture. I have answered your question, or it's.
I think yes, and the second one is the same. In fact, there is something which is strange to me when I see your image, is that I've already seen sometime that you have 2 spectra in an image, so in the slit, but in this case you have 4 of them. This is huge, but in fact this is due to the fact that you are exposing for a very long time. And in this case, well, I guess that you were in the Milky Way. I suspect. I don't know. I don't remember why is this spectrum. But of course, if you expose for a very long time, then you are exposed to have more stars in the slit, right?
Yes, of course, yes. But if you have too much stars in the slit, the main difficulty is to find a background sky. Background sky area without any stars. So, for example, in blue, you can see the background sky that I use to remove the background sky, but I try to have an area without any stars for subtraction.
Another question. So will the UVEX replace the LISA, or does the LISA have capabilities that the UVEX don't have? This is a very important question for me. In the product range that we're building, the LISA will remain, because the LISA will be is still today the most efficient instrument for faint targets, as Olivier said. And this is for very simple reasons linked to the optical architecture of the instrument, because mainly we have a focal reducer inside the Lhisa that makes it very efficient for fine targets. Okay, and we don't have this focal reducer in the UVEX, because I explained that in the UVEX, which is a Chojnowski architecture, we use the symmetry of the system to correct most of the optical aberration. So it means that we cannot have a focal reducer inside the instrument. Okay, so for me, really the product range we have today makes sense. So we'll have in the middle of this product range I mean for the high performance instrument, we'll have the UVEX, which is really a multi-purpose instrument which has the capability of a higher resolution than the Lhisa. Okay, so we can have the resolution of the Lhisa, but we can also have a higher resolution. But so this is really a multi-purpose instrument, and we can do a lot of things. But if we are looking for high resolution, then the Lhires III will be better. And if we are looking for low resolution and really faint targets, like all what Olivier and Pascal Ledoux are doing, the Lhisa remains the best one. So all these instruments have their place in our product range. Another question, is there any plan to create a remote focusing solution for the Lhisa? Or is that the reason for the UVEX? So it's not the reason for the UVEX, but what I know is that from now, all the instruments we will make, again, in the performance product range, they will all have the remote capability, and then the capability to remotely control the focusing. But so this is not the case for the Lhisa, and well, we don't have any plan. I think it will be quite difficult to add this feature. Personally, I have a dream, which is that we could reuse what we are what we are doing right now for the UVEX, to apply it to the Lhires III, to have a remote control of the focusing. I think that makes sense because we have some room inside the instrument. But for the Lhisa, because of its architecture, it will be difficult. And if one day we have to replace this instrument, and again, there is no plan so far, I think it will be a very different instrument, in fact, because it will be very difficult to have this capability. I hope I've answered. Olivier, there is 2 additional items on your Lhisa. What are they?
I put on my Lhisa, in fact, a remote control for open the garage door, for example. It's an infrared remote control. It's just to don't have to put your finger on the Lhisa to take reference, to take a calibration image, argon in neon lamp or a tungsten lamp. So I can, it's not a very long distance, but about 5 meters, you can remote control the argon neon lamp on the tungsten lamp. But because I use it before that Sheliak now sell the SPOX module, and the SPOX module do exactly the same. You put the SPOX module close to your laser, and you have an ASCOM driver that you, on your computer, you can control the 2 switch of the Lhisa spectrograph.
Thank you, Olivier. I think that we have replied to all the questions. We are on time. We are even slightly in advance, if I'm right. Maybe we can start the break now, and we come back if you don't have any other questions we come back at 20 p.m. UTC. Well, by the way, in France, it will be 9 p.m. Depends on where we are, when we are. So it means that we come back in 20-25 minutes from now. And until then, we have a small break. And anyway, if you want to continue to ask questions, we can continue. And thank you very much, Olivier, for this great presentation.
You're welcome.
Olivier, do you want to share the break slides or do you want me to do it?
Can you do it? Yeah, I think
okay.
You'll be more comfortable to do it.
Okay.
Thank you. Perfect. Thank you. I can see it.
See you at 20 then.
Yep. 20.
Hi, guys.
Hi, Tony.
Hi, Tony.
Hey, Tony.
Well, I see that the number of attendees in the main webinar is growing, so it means that people are coming back to this main session. We still wait a little bit for all of them.
Great
and
talk, Tony. Well done.
So I know that, well, so Tony, you're finished. I know that the e-shell talk is also finished. So in few minutes, we will start.
You hear me, Francois? David
Yes,
here.
I can hear you, David.
When do you think you'll be producing price information for the UVEX?
I got have the price, and the first the run that we're launching is at 3,800 euros the unit.
Right. Is this on the website or?
No, it's a secret. I hope that nobody is listening to us.
Okay.
I think the secret's out.
Yeah, you know, this is very important, the privacy these days.
Yeah.
Any well, Ken, I hear that you are online?
I am here. I'm online.
I think that there is still some people we wait.
Sure, why don't we give it another couple minutes, just in case some people are still on the break or still transferring over from one of the other meetings.
Yeah, they usually have some trouble, so let's wait a couple of minutes.
Yeah. And the people have to recover all the addresses, the links, and so on. And
So Ken, I wasn't able to get through. It showed up as
sorry, Albert.
Showed up as an image, and I probably made errors trying to tell an I from a 1 and a 0 from an O.
Well, sorry. At least there'll be a recording.
So I will stop sharing the break slides and leave it up to you guys. So when you want, you can start.
okay. I say 1 minute again, and we go. So well, Tony, you are connected. You are back here. I don't see Olivier Tizi back in the main session. I don't know if he plans to come. Anyway, so we can start again to keep the timing okay. So I hope that most people are now back to this main session after the different breakout sessions. And we will finish today with a presentation from Woody Sims. And so Woody, you are very involved in spectroscopy also for many years now. We had the opportunity to meet several times. And well, I don't know what I can tell about you, but I know that you are very involved in a lot of observations, and you have created a small groups where you are sharing all your experience with a group quite often, and this is impressive. And I know that you are a fan of the LISA instrument, which is great. And the only last thing I know, because we met several times, and you asked me to do it to tell it is that you are really a nice guy, and this is a pleasure to give you the mic. Thank you, Woody.
Thank you, Francois. All right, I'll share the screen, see if that works. And is that coming through?
Yes, I can see your screen. Yeah.
All right. Well, hi, everyone. My name is Woody Sims, as Francois indicated, and sometimes I go by Forrest. You might see that on the bottom of the slides. And if you want to send me donations for this talk, just send the checks to Forrest Sims. It's easier to cash them. Anyway, thanks for hanging in there today with us. What an honor to follow beyond or after Olivier Garde. I learned a few things and had to quickly adjust some slides for my presentation. My observatory is in a suburb east of Phoenix, Arizona, and I pretty much gave up on imaging because of the light pollution some years ago. Fortunately, spectroscopy came onto my radar. Spectroscopy is totally viable here because the spectral processing software created by Christian and by Francois, the Dimitri code, allows us to practically eliminate that problem. The image you see on the left is one of the first spectra that I took, and it's still one of my favorites. I used a Star Analyzer 200 grading with a color CCD camera on my C11. Incidentally, I purchased the Star Analyzer and RSpec software from Tom Field, who spoke earlier in this workshop. Thank you, Tom, for launching me on this amazing adventure in spectroscopy. And maybe you can even see back there in the back on my wall is Tom's Spectral Atlas poster. It's really cool. Let's find cursor control here. There we are. So I've put a circle around the star in this image, and this is a Wolf-Rayet star. And this is what I was going after when I took this image. And if you look them up in Wikipedia, you'll find they're a very peculiar, very rare star. And they have an unusual spectra that shows prominent emission lines of highly ionized helium and, depending on the subtype, highly ionized nitrogen or carbon. Well, that kind of sounded like science to me, and that sounded maybe like that might be a more interesting thing to look into than just taking pretty pictures. So this inspired me to see if I could produce scientifically useful data. Since that time, I've made some mistakes, like the discovery of the element unobtainium. I think David may have also discovered that. He mentioned that yesterday, I think, in one of my spectra. It was actually a cosmic ray. But I've also produced some useful scientific data, and some of which has been used in astronomers' telegrams and professional papers, and maybe historically that data and others will be used in future papers. So I'm going to assume at this point in the workshop that you have a pretty good idea of the terminology and the how-to of taking spectra. I'll use some terms interchangeably, such as images and exposures. So in the next 40 minutes or so, I want to concentrate on showing you some of the tools and the planning process which I use to get the best science data that I can with my equipment. And the last several slides will give you a list of links to some of these tools and resources, so you don't have to worry about trying to scramble to write things down if you're interested in something. I hope this session will help you achieve the same goals with your systems. So we're hoping the slide will advance here. That would be fun if it did so.
Well, for the moment, I still see your title slide.
Yes, of course, because it's not advancing. This would be termed a technical difficulty. Huh.
Yep.
Well, that wasn't because I pushed the arrow key. I don't know what happened to the arrow key, but anyway, note the catchy title for this session. And I'll be the first to admit that how to organize an observing session sounds deadly boring. At least it does to me. Ken, how on earth did you talk me into doing this? But okay, let's get started.
Persuasive.
Let's get started. I'll try to convince you that organizing and planning your observations will be worth the effort. This is not going to work if my slides don't advance. What are we trying to accomplish in an observing session? We need to get the best quality data that we can that allows us to accurately wavelength calibrate our target spectra and to correct it for the effects of instrumentation and atmospheric conditions. This latter part you'll hear me refer to later as response correction, the same response correction that David Boyd mentioned yesterday in his talk. So a well thought out plan is the way to get this done. Planning looks like a lot of work, but as in many things, a good plan can end up saving lots of time. Precious time at the telescope on a clear night and time in processing the data later. So what does it take to plan an observation to get good data? When you boil it down, there's basically three parts. Figure out all the tasks that have to get done, figure out what order to do them in, and estimate the time required to complete each of those tasks. Basically, a plan is going to allow us to get from a Park telescope to spectrum submitted in a database. The entries that you see here circled in red are spectrum of T Corona Borealis. This is data that's in the AAAVSO database, and you've heard a number of people talk about the AAAVSO database over the last several days. And so here's a couple of entries back this summer. And the one I'm going to use in this example is that observation that in UT time was on July 1st. And since this is sort of a hardware day at the workshop, it's always fun to see hardware. Now, those of you that were in Olivier's session before mine, this will look amazingly similar to his slides, but for the others that were in some of the other breakout sessions, I'll quickly go through this. And I found these really cool red arrows. So here's my Lhires-Lisa spectrograph around R = 1000. And with it, I've been able to reach targets as dim as about magnitude 15. Not a high signal to noise ratio, but sometimes that's adequate to get good scientific information. This is the calibration module that Olivier mentioned that has both a tungsten flat lamp in it and it has a neon argon lamp in it. And I control these remotely, as Olivier indicated. There are ways to do that without having to physically touch those buttons to turn them on and off. I use an ATIC 414 science camera. It's a monochrome camera. And I've got a Starlight Express Lodestar X2 guide camera. I also use a rotator, and I use this rotator to correct for issues of parallactic angle. And there's a whole, can be a whole discussion on that. But for targets that are low in the sky, it's important to orient your slit such that it's perpendicular to the horizon. And so I will rotate my spectrograph to do that for targets below 60 degrees altitude. Now it's real important if you're down in the soup in 30, 40 degree altitude to do this. And you can also use this rotator, as Olivier indicated, if you want to try to put two objects that are close together onto the slit. Now the second picture is expanded out a little bit. You see the Lisa spectrograph in the back, and in the foreground, that's a filter wheel, and I've got V, B, and R filters in there. And this is an ATIC 460 monochrome science camera. And these are mounted on a TeleVue refractor that's piggybacked on my main telescope, so that when I'm pointing at a target with the main telescope and I have a star on the slit in the Lisa, I can simultaneously be taking photometer information of that field and course, what I'm typically most interested in is photometry of that target star. And as David Boyd indicated, one of the methods of doing flux calibration is using a method like this with a V-band filter and simultaneously or near simultaneously taking photometry data. Okay, so here's some reasons I think planning each observation is worthwhile. Telescope time's expensive. Even if you own your own kit, it's still expensive. So you want to get the most out of it and your valuable time. Data quality, simply put, we want to get the highest quality data that our system can produce. We can do this by planning the best times for our observations and not forgetting any critical tasks. Problems. A good example I can think of for those of us with German equatorial mounts is the dreaded pier flip. Not good if a pier flip occurs or if you hit a meridian limit during the middle of taking your target spectra. Saving time. Much of the information from your plan can be reused in future observations of the same target. And frustration and embarrassment. Nothing like imaging the wrong star or forgetting to take an important neon argon calibration image when someone's waiting anxiously for your data. Okay, I made a slight change in the order in this slide. Avoiding frustration and embarrassment is probably the top of my list. You might think of preparing and executing a good plan as being like using an aircraft checklist for pre-flight, takeoff, cruise, and landing. For instance, we don't want to begin slewing the telescope before we've opened the observatory roof. That might be a little crude example, but it's good to have a plan. Okay, here's the spectrum of the symbiotic-like recurrent novae T Corona Borealis, as I showed you earlier in that database submission. This spectrum has been wavelength calibrated, response corrected, and calibrated in units of absolute flux. I mentioned earlier that we want to get an accurately wavelength calibrated and response corrected spectrum. How do we do this? To wavelength calibrate a spectrum, we need to take the spectrum of a reliable, repeatable, and convenient source with emissions at precisely known wavelengths. For many of us with Shellyak instruments, we've got a calibration lamp built in, and that works very well. To response correct the spectrum, we need to take the spectrum of a known non-variable reference star. The response correction process allows us to make corrections necessary to account for the effects introduced by our CCD or CMOS camera, our grating, optics, and importantly, the atmosphere on the night of the observation in a direction near to our target star. And I'll show you in the next slide what that might look like if you don't response correct the spectrum. Okay, lastly, you may want to, at some stage, acquire data which allows the absolute flux calibration of the spectrum. And you can see the result of all three of those things in here. So I pointed out some important helium lines and some hydrogen lines in the spectra. That's the wavelength calibration part that I'm talking about. The response correction is what allows us to get an accurate exo-atmosphere view of what the continuum of this spectrum might look like. And then over here on the left, you'll see that I have the spectrum flux calibrated in units of ergs per centimeter squared per second per angstrom. So that's the target. That's what we're trying to get with a good plan. Okay, this spectrum, I reprocessed this data on T Corona Borealis, and that blue line is what you get, or what that spectrum would have looked like had I not done the response correction. So each observer taking a spectrum of this target on the same night would get their own blue curve, which would be different from mine. But with each observer also taking the spectrum of a reference star with their equipment, calculating and applying the response correction curve, our data would now be comparable, just as if they were all taken exo-atmosphere with identical equipment. So these are some situations where the analysis you or someone might want to do with the spectral data does not require response correction. There are some situations where you don't need a response corrective, but most of us with low resolution, full visible spectrum range spectrographs, it's important to do this response correction. Okay, as David Boyd described yesterday, when submitting spectra to a database, some requirements will be imposed and possibly some additional recommendations. The bias and darks can be taken in advance, and the flats should be taken the same night as the observation. Wavelength calibration requires taking images of a calibration lamp. As I'd indicated, I use the neon argon lamp in the calibration module attached to my Lisa spectrograph. Others have got good results holding a lamp in front of their telescope. Response correction, I use reference stars that are typically in a V magnitude of 5 to 6. And so the exposures are usually pretty short because these are pretty bright stars. And so my reference star exposures are usually between 30 and 60 seconds. Good signal to noise is something you'll have to spend some time to determine good exposure time values using your equipment and the wavelength range of interest. One of the important things you can do, regardless of your particular equipment, is to take more exposures. I typically take 7 reference star exposures and 9 or more target exposures. Flux calibration involves gathering additional data near or at the time of taking the spectrum. And one method that I've described already requires collecting V filter photometry of the target. Okay, what can you do ahead of time? Well, you can create a library of bias and darks. I keep these files in a folder named CALIB for calibration in my target folder. These are typically good for several months, as long as you continue to use the same binning and camera cooler temperature. Flat lamp exposures should be taken the night of the observation and at the same temperature as the bias and darks in your library. I usually take them at the beginning of the observation, and I find that 12-15 second exposures for my flat lamp produces a good flat. But I want to point out in a talk yesterday from Olivier Garde that he takes 40 flats, so I may have to up my game on that. Thanks, Olivier. But in the interest of getting the best science data, I'm going to take a look at that seriously. All right, cal lamp exposures. For my system, again, with the neon argon calibration lamp, 30-second exposures work well. And I have a more detailed slide coming up on this. I slew at a slower rate than my mount is capable of slewing. And I have only a 6x8 arc minute field of view in my guide camera to work with. So you need to allow time to be sure you've found the correct star. And you need to account for this in planning your observation. I use my telescope jog controls to move the star forward toward the center of the slit. When I get close, I use PhD2's sticky lock feature to drive the star to the precise center of the slit. As I mentioned earlier, I use a rotator to mitigate parallactic angle issues. This takes some additional time to rotate and recenter the star on the slit. And magnitude limits. If the star is too bright, you'll have to pre-construct some means of blocking some of the light. If the star is too dim, you'll not be able to guide well enough or have enough aperture and throughput to get data with a usable signal to noise ratio. Okay, let's take a moment to look at a single flat image. To determine a good exposure time, you'll want to aim for 35 to 45,000 ADU counts in the brightest portion of the image, which in my case is in this area right here where the red circle is. And again, I'm taking 15-second flats, and that usually takes me an elapsed time of less than 5 minutes. But as I said, after Olivier's presentation yesterday, I'm probably going to be taking more flats. For the calibration lamp image, you want to take a long enough exposure to bring up the ADU counts in the argon lines, which are down here in the blue end of the spectrum. where the camera and the OTA sensitivity is typically lowest. In doing so, it's okay if you somewhat saturate some of the brighter neon lines here in the red portion of the spectrum. But overall, for my system with my bulb and camera, a 30-second exposure produces a good result for a calibration frame. So let's summarize what we've determined in advance so that we can plan our first observation. Maybe I should go backwards there. Biases, take 50 or more 0-second exposures in advance. Darks, take 15 or more 600-second exposures in advance. And I chose 600 seconds here because I can easily guide 10-minute exposures. And with the light pollution that I have, longer exposures are probably not a great option. But whatever your maximum exposure length time is, take darks at that time, and then the spectral processing software that you use will scale that appropriately should you be taking 300-second target images or 120-second target images. The flats, again, I'm going to take 15 or more 15-second flats. And as I said, I usually take them before, but they can be taken between observations or even between the reference and target star if you plan it that way. The reference calibration images take a 30-second neon argon exposure. And for the reference star, I do this immediately before the reference star. And for the calibrating the target star, I take a 30-second neon argon exposure before, and I take one after. And part of the reason for that is that target star exposures are the sequence, the elapsed time is going to be typically longer in the order of 15 minutes to a half hour to an hour and a half. And during that time, there can be some flexure in the instrument, and certainly there can be some impact from temperature changes. Okay, I promise this is the last slide with lots of text. So these are the times we need when constructing our plan and schedule. So for flats, I allow 5 minutes to complete that task. I allow a minute for each calibration image. That includes turning those lamps on and off, as well as getting the 30-second exposure. For the reference star, in my plan, I allow 4 to 8 minutes, which allows me to acquire 7 30 to 60-second exposures. For slewing and centering the star on the slit, I allow 5 to 10 minutes to do this. And that gives me time, and if I'm lucky, I can plate solve that image in the guider, and that makes it very quick, and then I'm just ready and waiting. If I can't plate solve the image, I'll show you some other ways to deal with that, but it takes a little more time to confirm that you've got the right target. Remember, we want to avoid embarrassment and get that star on the slit. And then for the actual target star, again, I allow 10 to 90 minutes plus to take 9 up to 600-second images. And sometimes I'll take more than that if it's a very faint target. So you allow that total elapsed time into your plan. And then I typically plan for a 15-minute period between the beginning of the reference star and the target star start times. I'd suggest maybe starting with a little larger gap than that at first, maybe 20, 25 minutes. It'll be a little bit more relaxed, and you're less likely to sort of get frustrated and blow out your plan. But I think as you gain more experience, you can get that down where you can kind of pre-plan those things at 15-second differential time, 15-minute differential time. Okay, so now for a short break after all that text. Note the full visible wavelength spectrum. The spectrograph has picked up some nice blue colors up above there. There's some nice values in green down below, and some red colors in the middle of the spectrum. By the way, this is my wife kayaking on the Colorado River near Lee's Ferry. Okay, some places for ideas if you cannot decide on choosing a target. There's an awful lot of stars out there, and you know, you've heard some ideas in this session already. And so I'll re-mention the astronomical ring for access to spectroscopy, or AAVSO. There are suggestions there on targets. There are priorities on targets. It's a good place to find a star to look for. The BESS database has a very refined system, as you've seen in previous discussions in this workshop, for looking for a star that might fit your magnitude capabilities in your instrument. Astronomer's Telegram is an interesting service if you want to hop on something that has recently been discovered, and maybe be able, depending on the nature of it, you might be able to contribute some data as follow-up for that target. AAVSO alerts can come right to your email, and there are suggestions there on the need for photometry and spectroscopy targets. And then I'll just throw in a completely different idea. There's a wonderful book called Astronomical Discoveries You Can Make Too by our very own Bob Buckheim. And he's got some interesting spectroscopy projects and ideas in that book. So that's worth taking a look at that also. Okay, I guess I skipped a slide there. So we should have a whole session in the future, in a future meeting on choosing a target, but we need to get back to organizing and planning our observation. And AstroPlanner is where I start. You can load up AstroPlanner in advance with multiple objects and what's referred to as a plan. And you can create multiple plan pages. The page you're seeing here is where I have put all the symbiotic stars and novae that I might be interested in observing. And I have another page in AstroPlanner for H2 type objects, and you can set up many different pages. You do not have to type in all the information on these targets manually. There are numerous catalogs available in AstroPlanner that you have access to, and it's very easy to download individual target data directly from Simbad. And I'll come back to Simbad shortly. You can easily sort the entries by any of the column headers that you see here. And I'll often use this feature to find a target in my list that fits my available observing time. And in some cases, I'll use it to find a target that is in a place where I don't have a cloud bank. So I might sort on altitude and then look down through azimuth and find a target that's in that portion of the sky that's clear for me. And again, I'll use T Corona Borealis as our target. And I've got that circled right here. You see information on it. I've set the lat long for my observatory through the site field up here. And one of the things that's nice about this tool for planning is that you can see this little graphic right here. This is the altitude over the evening of my target in the red plus marks there. And so somewhere in this 2100, 2300 time period is a time period I can catch that target at a pretty high altitude. And then over here, just from more of an annual planning point of view, you see a full year calendar, and you can see that in the late May through late July is a time that you can catch this target fairly high in the sky. Another important thing I want to point out in here is the air mass. And I've got the date and time of July 30th, and this is in local time and 9:35 p.m. observation time. And so for that date and time, I see that T Corona Borealis is in the southeast, and it's at an altitude of 82 degrees and air mass very near 1. All right, so that's great. So here's another planning tool from the Isaac Newton group of telescopes. This is free, and it's pretty simple to use. You can put in a latitude and longitude for your observatory, or you can choose a nearby observatory from the database list that they've got. And this Kitt Peak Observatory is fairly close for me. And you can put in the RA index for your target. And you can put in a date and time. And I've also put in the RA and DEC values for the star that I'm considering using as a response star, actually the one I used in this observation, but I wanted to show you this tool. And so you can see here, this again is on June 30th, and here's 2100, 2300 hours, just like we saw in AstroPlanner. And you can see the altitude versus time plot here, this top #1 curve. And then here's the curve for my response star, or the star, my reference star that I want to use for response correction. So it's a pretty good match that I'm going to catch it, be able to catch them pretty close to the same air mass, which is real important. Okay, you want to research your target. Olivier and others showed us SimBed yesterday, and SimBed allows you to enter an object name in this field right here. And I entered T Corona Borealis, as you can see on the left here. And this will come up with a lot of information, including a precise right ascension and declination for your target. You'll see that it's thought to be an M3 giant star, and there's some radial velocity information, and there's some magnitudes for some different filters on here. And we'll note that it shows a V magnitude of 10.247, and I draw your attention to that because we're gonna see that you're gonna want to check for a more recent value on this when you actually go to set up your observation. And while we're here, I want to point out this Aladdin Light tool over here on the side. I don't know how many of you have used this, but it's free, and you can click on that, and it will pull up an image that shows your target and shows some of the stars around it in the field. And this is one tool you can use to help you, particularly if you can't plate solve the image in your guider, or if you're having some trouble finding your target star, you can use that display right here in Aladdin Light. And there's a number of catalogs that you can overlay onto this display. And so this is a free tool. It does require an internet connection. And there is a locally installed version of Aladdin that's got quite a bit more capabilities. And I also use that fairly frequently, and that's free. Another wonderful, wonderful tool provided by our friends in France. And one of the things that you can do in Aladdin Light is you can scale this. So you've got those plus and minus buttons on the side, and some observers like Sean Curry uses this display on his iPad when he's at his telescope. And he uses that to, again, help confirm that he's actually found his target and able to put it on the spectrograph slid. So the point for our purposes is to give you information to efficiently find your target in your telescope pointing images. Okay, I'd mentioned that magnitude issue where we saw V magnitude in SimBad. If we go to the AAVSO photometry data, and this is looking at it for say 90 days or something coming up to the period of time that I'm taking the image, we'll see that it was around 10.1, and it peaked somewhere maybe 9.6, 9.65. And this most recent entry before my spectra, the planned observation, it's around just a little dimmer than 10th magnitude. So that may be a factor in determining your exposure times. Now, that's not a big difference, but some of the stars that we work, particularly some of those that are really interesting, can have pretty large changes in magnitude over a pretty short time. And so you may have to adjust your target exposure times in your plan because of that. So checking this AAVSO photometry data is very helpful. Okay, so what about the target exposure time? It's one of the elements in the room that we have to figure out. How long an exposure do I take? We've checked the recent AAVSO photometry, and through some previous testing, we have a sense of our magnitude limits for our system. The problem for this target is the H-alpha line. Now, this may not be for all the different kinds of stars that you shoot. They don't maybe have a great big H-alpha emission line, but many that I do have such a feature. So looking at the raw image, you can probably see that it's much brighter than any of the points on the continuum. And it's borne out in the spectra, as you can see there. So we've got this really bright spot here, and we've got this peak right here. And so what we want to be very careful of is that we don't saturate that H-alpha line. So the first time we come to a target like this, we may need to take one or more test exposures. But we want to choose an exposure time that gets our ADU count for, say, a 16-bit chip up, into the linear part, but the high end of the linear part of our camera, maybe up to 40 to 50,000. And in this way, we're hopefully are going to get enough photons in the rest of the spectrum down here that we get a decent signal to noise ratio. So I found for my system that 300-second exposures work well for this target when it has a V magnitude around 10. Okay, and while you're at the AAVSO website, I recommend you use the variable star plotter tool to print out a star chart for your target, and if necessary, your reference star. Again, this can save a lot of time if your pointing's not so good, or if you're looking for a target in a crowded field and you haven't been able to plate solve your guider image. So it's a good idea to choose a field of view in arc minutes that's a little bit larger than the size of your display on your guide camera, so that if you're not quite in the right place pointing wise, you might be able to pick up something in the pattern of what you do see and find it on this printout, and that'll help you push that target star to the center of your guide camera. And then set a magnitude limit for your target that's a little bit dimmer than what you're looking for, but not so dim that you end up with a million stars and a black piece of paper printed out. Okay, the target, we've got the target star, and I've chosen a start time of 9:15 p.m. when we'll begin taking spectrum of the target. So we need to identify a suitable reference star for response correction. And I'm going to show you two of the tools that I use for this purpose. And just as a reminder, the idea behind the reference star is that its spectrum is known and thought to not vary. Okay, both of the tools I'm going to show you make use of one or more sources for potential reference stars by using libraries such as the Pickles library and the Miles library. And the software that we use later for processing the spectral data, such as ISIS and Demetra, includes spectrum from these libraries.
Woody, sorry to interrupt you quickly. You have still 5 minutes, if it's okay for you.
I have only 5 minutes? I thought I had till the top of the hour. Okay.
Well, on the planning, well, anyway.
This is the reference star finder tool created by Francois Cochard. And I've entered in the latitude and longitude for my observatory over here. I've entered in the date and time of my observation, and notice this requires that the time be in UT, so I've added 7 hours from the time of my, for my site in Phoenix, Arizona. And so for a 9 p.m. local time observation on June 30th, I need to choose 0400 on July 1st. And when I click on the compute button, I get this display here. And this basically brings up all the candidates that I might consider as a reference star for this observation. And there are many things to consider when choosing a reference star. And we've had more than one multi-hour discussion on this issue and do not have time in this presentation today or even in this workshop probably to cover that. So it's best to say that choose a late B or an early A main sequence star at or near the same altitude and air mass and azimuth as your target. And so for T Corona Borealis, for the example we're discussing today, I chose this first star on the list, HD 143894. And again, it meets many requirements, but one of those is that its altitude at the time I'm going to take it is near the altitude of my target star at the midpoint of the elapsed time that I'll be on that target star. So that's an important part of our plan. Okay, the Mile Search tool created by Paolo Berardi and Marco Leonardi is another great tool that does a very similar thing as the Reference Star Finder tool. And again, you can see that I've entered the latitude and longitude for my observation site over here. And in the upper left, I've got the time, and this one I can put it in local time because it looks at my computer time. So I've got 9 p.m. local time for finding a reference star. And one of the really nice improvements in this latest version of this tool is that they put this Simbad button in here. And I can just click on Simbad, type in TCRB, and it will go find it and populate this information over here, which saves time and reduces errors in typing in otherwise the REN deck values for your target in this tool. So that's been a fantastic addition to this tool. And both of these tools offer some filters to increase or reduce the number of potential reference star choices. And in that vein, another feature in this version of this tool is this Simbad object column right here. And I'm really happy to see this, and at the same time, I'm kind of discouraged because it's reduced the number of stars that probably would make a good reference star because they have characteristics that might cause a problem, such as being a spectroscopic binary or a horizontal branch star. Those don't sound like they're guaranteed to be nice, stable, steady reference stars for our purpose. Okay, now that we've got a target and reference star, and we know the time required to collect the data, we're going to take 7 20-second exposures in this case. And usually I'd try to get a 30-second minimum, but that reference star I chose was pretty bright for me. So to not overexpose the reference star spectrum, I'm going to take 20-second exposures and 9 300-second exposures on the target. We've already estimated in advance the time required for flat and calibration exposures. We know how long it takes to slew to a star and place it on the spectrograph slit. All we need to do is put all this stuff together. Okay, so I created this document to help me organize and plan my spectrum acquisition. And the next one I'm going to show you is I'm going to pre-fill that in. And you'll see here I've got the date of the observation. And to tie this back in to what we've covered quickly here is I'm going to take the reference star exposure. I'm going to plan to take it at 9 p.m. I'm going to plan to take the target exposure at 9:15 p.m. And so what I've got in here is the name of the reference star, spectral type, its magnitude, EB minus V, and the air mass of that target, which was about 1.04 at 9 p.m. And you remember when we were looking in Astroplanar that we had an air mass of very close to 1.01 at 9:35 p.m. is the time I had an Astroplanar. And I picked that time because it's sort of midpoint between the time I planned to begin taking spectra of my target star and the end of that. So I want to get kind of an average air mass for this observation. And that's what I use to help me narrow down my selection for this reference star. So the reference star and the target star have the same fields in them. The only difference being is that I only plan one neon argon image for my reference star, and I plan one before and one after for my target star. So execute the plan. And here's what the acquisition log sheet looks like afterwards. I've obviously filled in actual times for taking the reference star and the quantity of those images. I filled in the actual time that I started exposing on the target star and the actual images. I've also got auto guider exposure times in here for both the reference star and the target star. This is very reusable from one observation plan to the next on this target. It's really helpful to be able to just grab those things from a previous observation and use them. And then in here, I've been using ISIS for processing this data, and you'll see that I have what I feel are key things to note in processing the reference star, the tilt angle, the vertical coordinate on the chip, the position of, in my case, the 5944 angstrom line that I use in the wavelength calibration process. And I have that same information recorded here for the target image. And I use those things sort of from observation to observation on the same night and over different nights to see if there's some shift in my instrument or if I've accidentally bumped something. So this kind of a planning document has helped me not just with planning the observation, but in the processing of that data. And then up here, I show I've submitted that data to the ARS database in this case. And so I end up with whole binders full of these plans. And surely you could do this on the computer, but I found it really handy because I'll sketch in things like here. This is where the reference star showed up relative to the center of my guide image on the reference star. And here when I slew to the target star, that's where my target star was. And this helps me from observation to observation to find and be more efficient the next time finding that star and putting it on the slit. Okay, so again and again. So here's T Corona Borealis. This is just 7 observations, for the most part fairly spaced out. I took 37 of them I've completed this year. And I picked this one to show you all because this is a very interesting dwarf novae, and it's predicted is, I think Francois Tessier mentioned yesterday, to do something dramatic in the middle of 2023. So it's important to establish a baseline during quiescence leading up to this next outburst. And so I and many others in the ARAS group have been taking spectra of this, and this will be important baseline information when and if we get something exciting going on. And so to bring this back to planning and organization, I was able to reuse the information on this plan for, on earlier plans for each of the subsequent observations of this target. And here are some links to the tools and resources that I use. And you should be able to do a print screen, probably under Windows, to capture this if you're interested. But here's this link to the Astroplanar software. It's pretty inexpensive. I think it's about $55, and it does far more than I gave you a glimpse of what it can do. The reference star finder spreadsheet tool from Francois Tessier. Here's an article on the ARAS website describing it and a download link for the actual tool. And for the Miles search tool, kind of the same thing, a download link. And you need to download a copy of the Miles data. And when you download that, you need to put it in a subfolder created by the installation of the spreadsheet. So that's important not to forget both of those files. And then SimBad's been mentioned numerous times here. I don't know what we would do without all the wonderful tools that are provided there, but here's a link to SimBad and the AAVSO variable star plotter link. The Isaac Newton group of telescopes, that's where we had that thing that showed us the altitude of our star over time for our observatory location and date and time. And you've seen this link a few times. I'll put it in again for AAAVSO and for the BE star database. I didn't know everyone else was going to put all these links in, so I included them. And I have to do a plug for the Eruptive Stars information letter, where you can learn a lot about different stars that all observers in the AAAVSO group observe and see your data. Okay, thanks for listening. Now make a plan to get out there and take good spectra.
Mm-hmm. Thank you very, very much, Woody. It was a very, very interesting presentation. It reminds me that when you begin in spectroscopy, you are just fascinating, but what people are showing, and you say, well, I'm not sure I will be able to do such observations, but in fact you will do, and you just have to take some time and to put everything under control, but you will do it. And once it is done, really the next step is to be productive, and what we have described is exactly that. So how can I use the best of my time? That's perfect. If you agree, we can take a few questions because, well, this is the last talk. There are interesting questions. Well, the first one is, it was a question from David. I didn't interrupt you, but could you please go back to the slide just before the Astro Planner, if it's possible, and maybe we can put the slide while we take the next question. Can you still share your screen? Or you know, it is shared maybe, but
that slide.
Maybe the one before the Astro Planner.
That's the one immediately before Astro.
Okay, so let's keep it. Now, a question from James, exciting presentation. Can you perform an absolute flux calibration on your reference star based on V-band photometry and then apply a correction to your target spectrum and count photons?
Not sure that I understand the question, but what you want to do is you want to flux calibrate your target star. That's what the mission is to take spectrum of your target star, response correct it, and wavelength calibrate it, and flux calibrate it. And by taking that V-band photometry, you're able to take that information and perform some mathematical operations that translate that relative intensity into flux calibration. It really doesn't have anything to do with the reference star.
Okay, so you can do it directly on the target, and in fact, you never need to do the same. There is no interest to do it for the reference star.
No, if that was.
I guess that the question is because the reference star has a known profile, where on your target you may have an exotic spectrum. So it may give the impression that it is easier to do the correction on the reference star, but in fact it's not the case. Okay. When choosing the reference star, is it not only appropriate to look for an object at the same altitude, but also in the same field of view?
It doesn't need to be in the field of view. That would be ideal, but I guess it depends on how you define your field of view. In my case, I have a 6x8 arc-minute field of view on the guide camera, and it would be nearly impossible to be fortunate enough to get a reference star that's in that field. So no, you would like it to be close in azimuth and close in altitude, but we're talking about a few degrees, not arc minutes away from your target star.
Okay. Another question from Jose Luis. Can you comment on focus process, which software?
On the focus process?
Yep. How do you proceed? I mean,
how do I focus the Lisa spectrograph?
Yep.
Okay.
Well, I don't know. Well, there is I don't know what is the question exactly. If it is the telescope focus or the laser focus. So
Well, I guess I'll talk about focusing the Lisa spectrograph and hope that that's answering the question for this person and others that might be curious. But I take a picture of the calibration lamp image, and then I pick a line, and I use the 5944 angstrom line because it's sharp and clear for me. And I measure its full width half max using ISIS, and I record that value, and then I'll open up the two side doors on the side of the Lisa. I'll put a finger and a thumb in from each side. I'll rotate the optics just slightly. I'll put those two doors back on. I'll take another exposure of the calibration lamp. I'll measure the full width half max of that line. And, you know, it's kind of a thing like this. If it starts getting better, you're going in the right direction. When that full width half max value starts getting larger, you've gone too far, and you're going to have to come back a little ways and kind of settle where you think you are in the valley, where you've got the lowest full width half max on that line. And that's not dissimilar to using Focus Max or the plane wave software that I use to focus my main telescope. But that's how I focus the Lisa spectrograph.
Okay, and the question was for both, and also for the telescope. By the way, I guess that you also know your instrument, and you know what is the minimum value or the best value you should get for the full FWHM.
Yeah, that's important, and that depends on your camera chip pixel size, and so yeah, for me, I'm looking at values, full width half max values when I get the best focus of around 1.7. But if you have a different camera chip like the 460, that'll be a different value. The Lisa instrument is very stable mechanically, but there is some thermal expansion and contraction, and so this is something that I do have to. If I don't have temperature changes, I really have not had to change the focus. But when I get nights here in the Phoenix area where it can be 40 C in the day and 22 C in the evening, then I will need to go through this focus routine because the focus will change. And another way that you'll see this is in your spectra when you've processed them in Demetra or an ISIS, and you see a resolution dropping below 1000. Starts dropping down to 900, 800, then that's a really strong clue that you should have checked your focus, and you should do so before your next observation.
Okay, wonderful. There is a last question. Do you use the photometry instrument to confirm the position? I find it quite difficult to plate solve on the guider image, which is only 7 minutes area in this case. This is a question from Keith.
Yeah, good question. Yes, I do on some occasions. I have a good mount, but it's no mount's perfect. And sometimes I'll slew, there are particular places in the sky where it will not place anything on the guide image. And then it's like, okay, now what do I do? And I used to probably do what you do, is jog this way, go this way, and then think about optimal patterns of trying to find it. But with that, refractor bolted onto the side. It's very quick and easy to take an image. And if you can't pick it out immediately, you can plate solve that image. Surely I've got a 45 by 60 arc minute field of view on that TeleVue refractor. And I can use that to guide the star onto the guide camera image. And then from there, I can use the techniques I've mentioned in the talk, and with ending with PhD2, bringing it to the center of the chip. So good question.
And there is also a question, can you share observant data for doing science job? So there is somebody who would be interesting to have, I guess, raw data to play with the data and do their own calculation.
I'm sorry, is this a request for raw data from Elisa?
Well, I guess, I think this is for the LSI. It can be the same for a lot of instruments, but
yeah, I mean, I'd be happy to provide raw data. If I get an email address, I can communicate and send raw data of the reference and target stars and calibration lamps and such as that.
Perfect. Thank you very, very much. Thank you for this great presentation. Ken, I'll give you the mic to.
Okay, thank you, Francois. Woody, before we move on, I just wanted to read to you a comment from Patrick Kavanaugh, who said, I agree with James Lee. Woody's presentation was not only exciting, but so well mapped out that it made it easy for all of us, especially for us beginners, to follow. Congrats, Woody. So I agree with all of that. Well said. And thank you very much, Woody. So that's the end of day 3. Tomorrow is day 4, devoted primarily to software. We start out the day with a presentation by Catherine Blundell from Oxford University, which should be outstanding. And then David Whalen, who's an extremely good presenter, is going to give us a presentation on data reduction with Python. And then we'll have an opportunity to do breakout sessions again and look at ISIS, Demetra, or RSpec, depending on where your interest lies. And then we're super lucky tomorrow to be able to have Christian Boole and Valerie Dusno presenting about UVEX data reduction. And if anybody knows how to do that, it would be Christian and Valerie. So that'll be an outstanding session. And then finishing up the day tomorrow, we have Woody again, this time with Steve Shore. And Steve is a huge friend of the amateur spectroscopy community. He's an astrophysicist at the University of Pisa, and he'll be here tomorrow to help us understand, I'm sure, a lot of astrophysics. He's a very enthusiastic, interesting presenter, and lots of energy, and he knows pretty much everything about astrophysics. So tomorrow will be an outstanding day. I thank everyone, and we'll see you again tomorrow morning or afternoon at the same time. So take care, everybody, and thank you.